Hi, Prayush. Can you hear me?
Yeah, hi Srijit. Good
Hi.
morning. I can hear you clearly. Hope my audible.
Yeah,
My
you are
voice is
audible.
audible.
Yeah.
Okay.
So, good morning to everyone. We are about to start our day two of this workshop, NAR 2024. We will wait for a few more minutes to let the participant come in, and then we'll start. After yesterday's absorbing sessions, today we are also having in total 6 talks or lectures, and hopefully we will again enjoy this day. So let us wait for a few minutes and then we'll start. Hi Arpan, are you around?
Yeah.
Okay, yeah. So our session chair is also here. So let us wait and then I will hand over to you. Okay, good morning again to all. So let us begin the day 2 first session of NAR-2024. And I would like to thank all the participants who are actually very much cooperative. Yesterday's event where they went very well. So just to remind that if you are having any questions, you can type in the chat box, and if the speaker agrees or the chairperson feels that it has to be addressed at some point, it will be addressed. But we prefer not to interrupt during the talk. But we have a dedicated session at the end of the lecture, the 10-minute session. So the talks or the queries can be addressed at that time. Okay. So now I would like to invite Dr. Arpan Bhattacharya, the chairperson of this session, who is from IIT Gandhinagar, who is a faculty member in the Department of Physics there. His working area is ATS CFT, black holes, astrophysical phenomena like EMRI, etc. So over to you, Arpan.
Yeah, thanks. So let's start. Our first speaker is Prayush Kumar, and he is a faculty member at ICTS Bangalore, and he works in numerical and observational general relativity, including nonlinear simulation of binary dynamics. And today he will talk about challenges in computational astrophysics with black holes. Now I will hand over to Prayush to start the talk. Prayush, you can start.
Okay. Thank you so much, Arpan. Hope everyone can see my slides and hear me clearly.
Recording in progress.
Yes.
Okay. So good morning, everyone. And very thanks for the nice introduction. Today I wanted to talk about challenges of computational astrophysics, specifically with black holes. So to zoom in, I'll be talking about numerical relativity as it is applied to systems made of purely black holes, the status of the field, and where we are going in there. So to start with, let's put the problem into some astrophysical context. We know that we are observing gravitational waves from binary mergers, compact binary mergers, quite regularly with the ground-based interferometers nowadays. Black hole binaries emit gravitational waves, and they are the primary sources of these signals for the current terrestrial detectors. So these orbiting systems of binary black holes, they continue to emit gravitational waves, and as they do, their orbits shrink and they come closer to each other until they reach a point where they are close enough that they coalesce, or a common horizon or a distorted black hole is formed, as you can see on the figure at the right bottom, which then settles down into a Kerr black hole state at the end by radiating away its anisotropies, and again in the form of gravitational waves. So that's sort of the kind of system that we are interested in studying in full nonlinear relativity. Now, gravitational wave observations with LIGO have been many. Nearly 100 had been seen in the first few observing runs of these instruments. In fact, this figure here shows a collection of all the compact objects that have been seen by the ground-based detectors so far. So the ones in blue are all LIGO-Virgo observed black holes. The ones in purple are the black holes that had been observed before LIGO-Virgo era, specifically through indirect emission of electromagnetic radiation and so on. And the objects at the bottom in yellow and orange are neutron stars that have been observed over the past few decades. So the thing to note from this is that above, so I've drawn a horizontal white line over here. All the black holes that lie above that white line are massive enough that it is really the last stages of their coalescence that is visible to the ground-based detectors, which means the very last stages of in spiral, this merger portion as well as the settling down of into the final post-merger black hole. That is what comprises the major fraction of the signal that is visible to LIGO and Virgo detectors. Now, this fact is again illustrated here. So, for example, I've picked 3 specific binary black hole merger events. GW 150914, that was the very first event. Then GW 151012 and 151226. And they are sorted in order of decreasing total mass of the system. Now, the larger the total mass, the lower is the frequency, or the longer are the timescales associated with the system in GR. So the heaviest of these objects, they emitted at the lowest frequencies. So that would be the blue signal on the right, and the corresponding frequency domain signals are shown in the figure on the left. So on the left, you can see in the same exact colors, the 3 different signals overlaid on top of the LIGO-Virgo noise spectra, or which illustrates the band of frequencies within which we are able to see gravitational waves from these systems. So the main point, as from the previous slide, is that the more massive binaries we see, the more strong field, truly dynamical, nonlinear, general relativistic effects we actually measure, right? And that is good because that helps us understand gravity in its more and more extreme regimes. Okay, so what has been the role of numerical relativity in this science? So I've drawn a small flowchart here, and that depicts how from the level of observations to inference, what all other stages that information proceeds through. So to start with, at the top left, we have the actual compact binary source, the binary black hole source that is inspiraling and merging and emitting gravitational waves. These gravitational waves impinge onto this interferometric detector. The detector observes them. The data goes through a calibration stage. And that is where it is actually ready for some analysis. The first analysis stage comprises of a match filtering stage. And that stage uses a large collection of GR-based waveform templates, which are nothing but theoretical predictions of what these gravitational wave signals should look like, based on our understanding of these binary black hole, binary neutron star systems, right? Beyond this stage is a second stage, which checks for whatever triggers come out of the first stage. It checks whether those triggers are truly astrophysical in nature or not, and that's the signal consistency stage. And it also uses the same collection of waveforms from theoretical understanding of GR. After these 2 stages, typically we have a large collection of triggers coming out. Most of these triggers are chance triggers from pure noise events, and those form a background that is shown in red here. You can see the background has its own pattern as a function of the reweighted SNR corresponding to each trigger. And any real signal typically stands out far above this background. And that is how we know that we have detected a gravitational wave signal clearly. Once we have detected this, we take that specific chunk of data and we perform a detailed Bayesian parameter estimation on it to understand what was the nature of the original source that emitted this signal. So you'll see that in all these 3 stages, being able to model the waveforms is key. And that is where numerical relativity comes in. So numerical relativity is typically used to perform simulations of these black hole collisions, black hole neutron star collisions. And these collisions are then used to inform waveform models, which are in turn used to generate the large collection of waveform templates that are used by this machinery of GW astronomy. Okay, so numerical relativity really plays a central role in this science at the moment, especially because we have heavy black holes as the most popular sources of gravitational waves at the moment. Right. In fact, numerical simulations are indeed necessary for binary black hole science. That's because for the last several orbits before merger, for the merger itself, as well as the physics beyond merger, much of it can only be computed using fully numerical, fully nonlinear solutions of Einstein's equations. And this is the regime where analytical methods such as post-Newtonian theory breaks down. In fact, without using numerical simulations, many of our iconic GW events, like the very first one, 1509-14, and some others, would have been detected with much lower significance, sufficiently low that we may not even be able to claim them as the first detection, for example. And if 1509-14 source had been just a quarter further away than it was, it would not have been seen in Livingston at all, and therefore it would not have had any detection for that event. And even if we see all of these sources, all of these signals, without this high precision information from numerical relativity, we'll not be able to understand the qualities of the source very well. In fact, for example, this figure on the right bottom illustrates that pretty nicely. So if you want to measure the mass and spin of the post-merger black hole from these coalescences, with or without the results of these numerical simulations, what you get is the solid dashed curve versus the the solid curve versus the two dashed curves here. And you can see really this information about the late stage dynamics is key to high precision measurements of these parameters. Okay. And obviously, as a corollary of this is that this allows us to test GR, etc., in its most extreme and dynamical regime. Okay. So how do we simulate? So in the next part of the talk, I'll talk about how we simulate black hole coalescences. So to start with, let me show a visualization to talk about exactly what kind of simulations is it that I'm talking about here. So I hope you can see the YouTube video that I've just started playing here. Yeah. Okay. So what is being shown here is, oops. So what is being shown here is GW 1509-14's equivalent numerical relativity simulation. The two black holes are shown as the two horizons over here in the center. The color near the horizons, this is the spatial curvature, the 3dg scalar here. And far away from the source, the color is the outgoing gravitational wave. Okay. So, yeah. And note that the two black holes here are spinning and their spins are misaligned with each other. So the cross terms between the two spins will generate a top, which will rotate the plane of the orbit over time. And so you will see that as the orientation of this orbital plane changes during the course of this movie, right? Okay. Right. Okay. And the arrows here also show the rate of flow of time. The size of the arrow shows the rate of flow of time and the direction shows the direction of flow of time. And the movie slows down close to merger. So this moment is when, for the first time, a common horizon was formed. And it very quickly settles down into a curved black hole state at the end, right? And you can see the gravitational wave peaks and troughs that are being emitted and traveling outward from the source. Okay. So this is a typical result from a numerical relativity simulation for binary black holes. And the waveform that came out of this particular simulation was the one that was used in the GW discovery paper in the figure shown at the left bottom here. So in the top two panels is the raw filtered data from the Hanford and Livingston observatories. And at the bottom is the closely matching equivalent waveform from numerical relativity. Okay. We are also able to perform simulations of neutron star black holes and binary black holes, and I'm for just illustration showing one of those simulations here. So what is happening here is that we have black hole and neutron star, which is going to be tidally disrupted by the black hole as time goes on. At this moment, we can see the star as tidally disrupted. It forms a small accretion disk around the black hole. And as time goes on, all of the material falls into the horizon. Okay, approximation without the necessary ones to perform numerical simulations. Okay, just give me 1 sec. Hope you can still hear me. Sorry, I had a brief trouble with my microphone. Okay. So how do we do these simulations? How do we perform these simulations? So that's what I want to talk about in the rest of the talk. And so let's start. So what we are doing is actually we're solving the equations of gravity. We're solving Einstein's equations, which unlike in Newtonian gravity, which can be stated in this form, in Einsteinian gravity, the space-time itself is poised to be curved. And this curvature is represented by the metric of the space-time fabric. This metric is a tensorial field that is typically represented as a GAB tensor. And this field itself is determined by solving Einstein's equations, which is a set of 10 coupled second-order partial differential equations, subject to some initial and boundary conditions. So this is a highly non-trivial set of PDEs, and solving them becomes difficult in dynamical situations, and we'll see how and why in time. So the very first attempts to actually solve these equations were made as early as 1964 by Hahn and Lindquist at IBM. And they were able to actually evolve Einstein's equations for a very short period of time before the simulations crashed due to numerical blowups, and we'll see why that happened. In fact, the problem that infested their simulations remained an open problem for the next 3 or 4 decades. Okay. Until about 2005, when Franz Pretorius was able to perform the very first stable binary black hole evolutions. So here is the paper that he wrote that year. And the 2 figures here show the trajectories of 2 black holes and the associated gravitational wave emission from that system. Soon thereafter, different groups around the world were able to also simulate these binary black hole systems. So there'll be the RIT group, Georgia Tech, Maryland group, and others as well. So briefly speaking, solving Einstein's equations is the very first step is to break down the manifest covariance and break basically the concept of space-time into space and time explicitly. And that is because we are only capable of supplying initial data at one instant of time. So when we perform this 3+1 split, we find that the evolution equations, the Einstein's equations, they separate out into a set of 2 partial differential equations. The first is a set of evolution equations that tell you how the metric of the spatial slice evolves from one time step to the next time step, and how its extrinsic curvature, which is a measure of how the slice is curved when embedded in the larger space-time, also evolves from one time step to another. And then another set of equations that we get are the constraint equations, which are basically constraining the behavior of the curvature within a slice itself. So these are elliptic PDEs that must be respected or solved at every time step, while the evolution equations tell us how to proceed further in time given some initial conditions of your system. Right? So it's not unlike Maxwell's equations, for example, where you have evolution equations for the electric and magnetic field, but you also have some constraints that must be respected as time goes forward. So I have a question in the chat that I'm seeing. The question is, are these simulations performed using publicly available code? The simulations I described and showed, they were performed using the spectral Einstein code that I just talked about, and that is not publicly available. However, we are developing a new code base called Spectre, which is indeed publicly available. So I'll talk about that as well. Okay. So what makes this process challenging? There are many reasons what makes this challenging. The first of them is that we have many length scales in the system. We have the size of the black hole. Then we have the separation between the black hole, which is approximately a factor of 10 larger than the size of these horizons. Then the gravitational wavelength, the gravitational waves that we want to actually record may have wavelengths 2 orders of magnitude larger than the size of the horizons. So if we want to simulate them in a box, then that box has to be at least several of these wavelengths large in order to reliably extract these gravitational waves. So this puts a 3 to 4 order of magnitude separation between the smallest and the largest length scales that one must resolve at all times, right? Now, we don't know what coordinates to use. For a space-time, we don't know yet. If a priori, before performing a simulation, we don't know what coordinates would be better than others, which coordinates may or may not develop some singularity, some coordinate pathology or not, right? Now, the next would be, of course, putting black holes or singularities on a grid is always fun, right? Because computers really don't like infinity. So there are a few strategies which can help mitigate this. Now, the next problem, which number 4, is that Einstein constraints grew exponentially. And this is actually the key problem that remained unsolved for decades before Pretorius' simulations came out. So what was happening was that given some initial data, people were evolving the evolution equations. And soon, in a very short time of this evolution, the constraint equations became violated. And these violations, they grew exponentially with time, right? And that led to blowing up of the numerical solution, right? So you may ask, why don't we simply solve the constraint equations at every time slice? I think there's a question like that in the chat. And that is because this forms a set of tightly coupled elliptic PDEs that are very expensive to solve. So if we solve them on every time slice, we will simply make the cost of these simulations intractable. We will probably be able to do 1 or 2 simulations in a year or so. Right, so that's why. Next thing is resolving shocks and discontinuities in curved spacetime is a non-trivial challenge. And then we have the computational challenges, of course. So we are at any time evolving PDEs in 20 to 40 variables. And if we evolve time globally, then that global time step will be determined by the smallest length scale in your system. So that is not an efficient thing to do, especially because the accuracy that is required by the LIGO detector is quite high. We require the simulations to be faithful to much less than 1 radian error in tens of orbits long simulations. Okay, but one powerful technique that we particularly used are spectral methods, and they work quite nicely in vacuum when we have purely black hole systems. So this brings us to our particular group's efforts, which are in the form of a code called spectral Einstein code, which is designed to solve Einstein's equations. And it has been in development for the last 20 years or so, with more than 500,000 lines of C++, Perl, Python, and so on. And there are many institutions that are now part of this, but originally spec was written by developers at Caltech and Cornell. And ICTS is now very much a part of the group. So, yeah. Okay, so why do we like spectral discretization? Because the way we use spectral discretization is that any unknown field that you want to evolve, say U as a function of X and time, we decompose it in a choice of basis. such that the coefficients of our decomposition are really the true functions of time, while the basis functions are not. So they are only functions of space. This clearly brings a nice separation, neat separation between the time and spatial coordinates. And this also means that all spatial derivatives that we want to calculate, the spatial derivative operator passes through these time-dependent coefficients and only acts upon the basis functions themselves, right? So which means that we can compute the derivatives exactly, as opposed to finite difference schemes, where the field is represented by the actual value of the field at different points in space. And in order to compute spatial derivatives, we must construct local interpolants and differentiate the local interpolant. And therefore, the accuracy of that interpolant is restricted by how many points are we actually locally taking to construct it. If we want a higher and higher order derivative, the more and more points we must include in this interpolation. And that will increase the communication cost between points. Okay. Whereas for spectral representation, the solution is actually represented in these as the sum of these basis elements. Okay. The next part of how spec has become a robust code is choosing a carefully designed domain decomposition around the system that we are trying to solve. So this is what the domain looks like for the binary black hole problem. Around each singularity, we place a set of nested spherical shells that are shown here in the top left figure. Then between the two black holes, we place grids in this particular form. And then further out, we have a domain structure that is tailored to the near field solution. And far away from the source, we typically simply have concentric shells, because not much is actually happening here beyond the propagation of gravitational waves outside.
There is a question at the chat box.
Okay. Yeah. So the difference between finite difference and spectral approaches is, I think, visually summarized in these two figures, if you see carefully. In the spectral approach, your true solution, which is the red curve here, is represented as a sum of a linear combination of these basis functions, with the assumption that the solution is smooth, right? So because we are making this approximation, we can make such an expansion. And now, if we want to calculate derivatives, we can calculate derivatives simply by knowing the derivatives of our basis functions. So if our basis functions are Chebyshev polynomials, we know their derivatives. If their bases are Fourier series, we know its derivatives, and so on and so forth. Right? Now, in finite difference schemes, the field value itself is stored at every grid point as such. So calculating derivatives becomes expensive and error prone, which means that spectral methods for a fixed number of points, spectral methods are more accurate than finite difference methods in solving partial differential equations. Okay, we can talk about this in more detail. I'm going to skip over that and talk about the evolution equations. Okay, so I've talked about how we split space-time into 3+1. Now, given some initial data at some initial conditions of the initial state of the system, we want to perform an evolution of Einstein's equations. And we do that in a first order form. So we take the second order Einstein's equation, the evolution part of Einstein's equations, we reduce them down to a set of first order hyperbolic partial differential equations. And that's the form we actually use for our numerical evolutions. So here I'm writing the general form of a first order set of hyperbolic PDEs. So we have the time derivative here, we have the spatial derivative terms here, the contracted by this matrix, and the source terms, all the non-derivative terms on the right hand side over here. So for specifically Einstein's equations, the evolved fields U alpha would be the metric G AB, its time derivative pi AB, and its spatial derivative is phi IAB. But in order to turn the second order equations into first order equations, I'm sure you're all comfortable with, we have to elevate its first derivatives into free variables. So that's what we have done. So instead of just g as the free variable, we now have g and phi as three separate free variables. And so we get PDEs in all these three that are typically of this form that I've shown here. At least the principal parts of those PDEs, which mean all the derivative, all the terms that include the derivative operators, are shown here, right? And these equations are, of course, subject to constraints, such as the gauge constraint or the simple constraint that these definitions of pi and phi must be satisfied throughout the evolution, right? Because note that once we start evolving, it's not guaranteed necessarily that phi IAB, the free field phi IAB, will actually track the spatial derivatives of this free field GAB at all times, right? So this becomes an extra constraint that we must impose in addition to these evolution equations, typically, right? So what really happens is that if we write down the evolution system for these constraints, they turn out to have a term proportional to the constraints on the right-hand side. And this is the term that was responsible for the exponential blow-off of constraint violations for more than 3 decades or so. And this is controlling this term is what took the longest. It was one of the most formidable challenges in numerical relativity in the past, right? So how did we do it? How did people do it? In order to understand that, it's a procedure called constraint damping. I'm going to illustrate that using the scalar waves in flat space-time. So this is the second order representation of the scalar wave equation without a source term. The first step would be to reduce this into a first order form. So in order to do that, I have to introduce two new variables, pi and phi, which are respectively the time derivative of psi and the spatial derivatives of psi, right? And now the constraint I get is this, that my phi I, the free variable phi I, should track the spatial derivative of psi at all times, right? Now, if you write down the evolution equation for this particular constraint, you find that on the right-hand side, we have an identical zero. So it's not quite as bad as Einstein's equations where we had terms proportional to C themselves, but it will still do the trick because in case numerical violations of this constraint crop up in the scalar wave system, those violations will never ever leave your domain. They will just stay there. They will not decay away. Those errors will continue to roam around in your domain as per this evolution equations, right? So what we can do is modify the original evolution system such that by adding multiples of the constraint itself. Now remember, at the continuum level, the constraints are identically zero. So we are not changing the physical solutions of these equations, right? What we are doing is we are changing the solution space in a way that the physical solutions are becoming an attractor. Yes. So by simply adding this term on the right-hand side of just the third equation here. Now, if we write down the evolution equations for CI, we get an equation of this form, which of course has a solution where the constraint will exponentially decay on a time scale that is governed by this constant gamma 2. So now we have a knob gamma 2 that we can move around and we can damp away any violations of our constraints. Okay, so the same exact qualitative procedure is done for Einstein's equation. It's a little bit more complicated to explain. It may take a bit more time, but you'll see a few different combinations of multiples of Einstein constraints have been added. So these are the original first order PDEs of the evolution equations of Einstein's equations in generalized harmonic gauge, right? Earlier I had shown you only the principal parts. Now I'm showing you all the terms in the partial differential equations, right? And because of the addition of these crucial key terms, now the constraints, Einstein constraints, become proportional to these e to the power minus gamma naught and gamma 2t. And now just by controlling the values of these constants gamma naught and gamma 2, we are able to damp away constraint violations exponentially.
Sorry,
Okay, so I see another question in the chat. In the 3+1 decomposition in this case, does the boundary condition taken at t equals to 0 to infinity or minus infinity to infinity? So at the outer boundary, typically our boundaries, I'm going to talk about, okay. So at the outer boundaries, we typically we have to impose boundary conditions, right? So we impose boundary conditions only on the outgoing characteristic modes of the evolution equations. And we require that these outgoing modes continue to propagate out. They're not reflected back. So we basically want to have a evolution domain where the outer boundary is transparent. Modes that are traveling outward, they leave the domain and they never re-enter. They should not be reflected back from the boundary and so on. Okay. So how do we deal with the singularity? For the spectral Einstein code, we excise out the singularity. What does that mean? So we cleverly design a domain such that it extends inside the horizon, yes, but it doesn't extend all the way to the singularity. So if this dark blackish region is the world tube of the horizon, of one of the two horizons, then we extend our domain up until this red cylinder over here, right, which is right inside the horizon, but well outside the singularity that lies inside over here. So this also means that at this particular boundary, we don't need to provide any boundary conditions because there are no incoming or out. I mean, all the fields are mostly flowing out here, right? Nothing can come back in. Okay. Another key aspect of what makes spectral Einstein code robust is being able to adaptively refine the grid or the mesh depending on the needs of the PDE solver, right? So for example, one way of measuring error is by measuring how fast our spectral expansion coefficients are falling off. Typically, in a well-behaved smooth solution, the coefficients they can fall off exponentially. And at some point, we will truncate. We will choose to say, okay, we are only going to keep the 6 leading order terms, and that's it. Which means that the error we will accrue would be proportional to the highest order or the smallest coefficient over here. And this error is called truncation error. So we typically monitor the truncation error in all fields that we are evolving. So what do I mean by all fields? So we remember we are evolving the tensor G, the metric tensor, its time derivative pi, and the spatial derivative is phi. So gxx, gxy, gxz, say pi xx, pi xy, pi xz, phi x, tt, xxx, xyy, all of these components of all of these tensors individually are monitored at all times for their truncation errors. And the moment we find the truncation error has become unacceptably large, we refine the meshes in order to resolve that particular component of that particular tensor better. So typically what we find is that the AMR system, it places down a lot more grid points near the black holes. So in this schematic figure here, the two horizons are given here and here, right? This is the larger horizon, and this at the peak here is the smallest horizon. The height is the resolution, okay? So the resolution is lowest away from these two black holes, and it's more close to the bigger black hole compared to out away. And it's even more near the smallest black hole. And that's because the smallest black hole will have even the smallest length scales corresponding to the oscillations of its horizon that need to be resolved over here. Right? So this figure illustrates what I was talking about qualitatively. So for example, this is an actual set of spectral coefficients taken from a real BBH simulation. And these are the top, I think, 15 coefficients or so as a function of time, right? And this black line over here at 4800 marks the moment of merger. This is where the two black holes merge, right? So you see that the error actually corresponds to the highest order coefficient here. So the error grows, and as soon as it grows by a certain amount, a new curve appears, and that new curve appears because we've just added one more basis function to resolve that field. The error grows again, and we add more basis functions, and so on and so forth. The same thing can be seen in this figure here. So blue is the target truncation error, and the measured error oscillates like this, right? So this is one way of refining our measures. Another way of refining would be redraw the whole domain also, which is also something that automatically happens. Okay. And at all times, we need to track the parent horizons very carefully because we need to place our excision surfaces right inside these horizons. So any time we have errors in how well we are tracking the horizons, the excision surface may intersect the horizon, and that means now we may have incoming fields at some part of these excision surfaces, and that will destroy simply the solution. So this horizon tracking system is typically done in the following way. We represent the shape of the horizon in the form of an expansion in spherical harmonics, and the coefficients of this expansion we control using a feedback loop control system. Okay. So going back to the original list of difficulties, these were the broad difficulties that I had discussed. With the spectral Einstein code, we have more or less managed to handle multiple length scales. We've managed to figure out what are good choice of coordinates, how to handle the singularities in our system, how to control Einstein constraint violations. And what still is not very satisfactorily resolved is how to handle shocks and discontinuities, and how to make these simulations scalable and less expensive, keeping the accuracy requirements in mind. Right? So these are the outstanding challenges of the field. Right? So we go back to the drawing board and we take up only the outstanding challenges, which are the multiple time/length scales, computational challenges, shocks, and high accuracy requirements. And we realize that people need to sort of think differently in terms of the whole paradigm of how these differential equations are being solved. So we decided that going forward, we need to make 3 new paradigm choices. The first is entirely throw away the discretization scheme that we have been using, right? And we ideally want to use a discretization scheme that has high order accuracy while being local, while not requiring too much communication from its neighbors. Why? Because if you require too much communication from your neighbors, you increase the communication cost, and so your simulations are then sort of limited by how much communication bandwidth your computers have, and that will slow down your simulations significantly. The next paradigm that we adopt is an entirely new parallelization scheme that can actually scale, which the current scheme does not, and I'll describe it in a bit. And finally, instead of evolving time globally everywhere simultaneously, we can evolve time locally in different pockets of our domain and stitch them together as we go along. Right? So let me talk about each of these 3 together. And this is sort of the part where I'm describing what we are doing to solve to address the future challenges of the field. So now, these were the 4 requirements that we require from the discretization scheme that we want to use, right? So the first candidate we have are finite difference methods. So the domain, I've shown only a one-dimensional domain here. So the domain is a set of co-location points, and the solution is locally represented as a polynomial that interpolates through these grid points. Right? So now, in order to calculate derivatives, you must calculate this polynomial and differentiate that. So the accuracy of the derivative depends on how many neighboring points you stack together. right? So which means that while at low order accuracy, this discretization is local. If you require high order accuracy, suppose you require eighth order accurate spatial derivatives, then you no longer can call this a local sum. It will require communication from a lot of neighbors, right? Finite difference methods are able to handle discontinuities quite well, but they're also able to handle inhomogeneous grids, but not as well as maybe a finite element methods. The next candidate would be spectral methods, which we have been using all this while for binary black hole problems. And in this, the domain is represented by these separate elements. And within each element, the solution is expanded on a local choice of basis functions. So in each of these subdomains, I have shown the first two basis elements, the constant and the linear basis elements, right? So the true solution, that is the green curve over here, is represented by a combination of the constant and the linear element, right? Okay. So it is now a local scheme even if you require a high order accuracy, because even if no matter what order derivative you need within dk, you only need information within this element. You will not need information outside this element to calculate derivatives here, right? So it's local at high order accuracy, local at low order accuracies. It's able to handle inhomogeneous grids, but it simply cannot do discontinuities. It requires the solution to be strictly continuous at all the element boundaries, right? Which means this is perfect for smooth solutions, smooth fields, but it's not so great when your fields are naturally going to contain discontinuities. Now, this is not much of a concern for black hole simulations, but it's a large concern for any system which has, say, neutron stars in the picture. And if you remember the movie I had showed you earlier, the neutron star had gotten disrupted by the black hole that it was orbiting. And the process of disruption, for example, if we were using spectral methods there, would require re-expanding the solution at every time point and so on. I apologize if that last point was not very clear. We can discuss that in the after my talk. More depth. Then another candidate would be finite volume methods, right? So finite volume methods are simple to understand. So the solution is typically represented by cell averages within each of these sub-elements, right? So this is the true solution. And the blue lines represent the actual represented discrete solution over here. Now, they can obviously handle discontinuities, yes, but when we want to calculate derivatives, in each element, there is simply not enough information. So it needs more information from its neighbors, and higher order derivatives will require a lot of neighbors to inform. And therefore, if this is highly non-local at high order accuracy requirements, right? So finally, we come to the magic ingredient, which is a discretization scheme called discontinuous Galerkin. So these methods are not very old. They were developed in 1990s or so. And what happens in these is that just like spectral methods, the solution is expanded locally. In each domain, it's expanded in a local basis. But with the key difference that between the elements, an exact continuity requirement does not exist. An approximate flux of information is what DG methods require. So So this key difference with spectral methods gets rid of the handicap the spectral method had, which about handling discontinuities. And DG methods are actually local at low order and high order accuracy. And if, for example, if you want a high order derivative, just turn up the order of your basis in your element, right? And they can handle discontinuities, and they can handle inhomogeneous grids that you might require for tracking your system. Okay, so no spectral methods, no finite differencing. We'll go with discontinuous Galerkin methods, right? Now, the next new paradigm that I described was using local time stepping. So now let's just look at this domain for a couple of seconds, right? The two black holes, or to the two neutron stars, or whatever we're solving for, are sitting right in the center over here. We are not even able to see them at this level. Most of the domain is empty. All that happens here is the propagation of gravitational waves or electromagnetic waves, whatever they might be, outside, right? So trying to perform evolutions with tiny time steps, and by tiny, I mean time steps that are dictated by the length scales of the oscillations of the small horizon in your system. If we perform such small time steps everywhere, that's a terrible waste of computing. Right. So local time stepping can and has been achieved, and what really happens is if I reduce this 3D domain into 1 plus 1D domain, so space is along x-axis and time is along y-axis here, right? So what happens is that near the smallest length scales, we'll take small time steps. And for example, we'll take the smallest time steps near the smallest black holes. We'll take slightly larger time steps near the bigger black hole, and much larger time steps out far away from the source where we don't need to take very small time steps. And all the information that we need at these intermediate stages, we are simply able to extrapolate from the past information, right? So in practice, at the moment, we are able to achieve approximately a ratio of 16:1 time steps. So we can take 16 times larger time steps here compared to here, right? Okay. And finally, the last paradigm that we will need going forward into the future is how can we parallelize our calculations better? So currently we use a domain-based parallelization. What does that mean? So we have obviously split our entire domain into smaller elements. Yes. Now we take each element, assign that element its own computer, and that core handles all of the calculations associated with that element, right? So the problem with this design is we are thinking like physicists. We are not thinking like computer scientists here. So it's an easy design to think and implement about and think about and implement. But what in practice ends up happening is that the core that is assigned the smallest, I mean, the space-time region around the smallest black hole, it is typically the slowest of all. And everybody else finishes its tasks much earlier and then waits simply for that slowest guy to complete its work. So typically this leads to a lot of wastage of computing because of this global synchronicity requirement, right? So the new parallelization scheme that we embark upon is called a task-based parallelization scheme. And this is not something new in the world, in the sense that in the industry, it has been used in the past and it is currently being used at large scales. It's only in astrophysics that we have now recently started using it. And conceptually, what is happening is we have a computational domain here that is shown schematically. So we have some elements shown in blue and the boundary between the elements shown in purple here, right? So instead of thinking in terms of these elements, we now take the calculation requirements for all of these elements, put those requirements in a global object space. And then depending on how and when every calculation needs to be performed, any core can get a part of any of the calculation required. So what does that mean? It means, for example, when this fourth guy has done calculating the right-hand side of Einstein's equations in, say, this spherical shell, when it is finished with that, it will go and help the core that is calculating the right-hand side closer to the smaller black hole. It will not simply sit idle, right? So this is called task-based parallelism. All the tasks or the computing tasks are put into a global queue. And from this queue, the tasks are popped and pushed to various cores as and when they become available. So really, no code is ever allowed to sit idle and so on. And this can be quite a game changer. So wheels I described are leading to this future generation code that we are currently writing, and it's in its advanced stages now. It's called Spectre, right? And here I'm showing some scaling test for Spectre. So typically when we run spec or any other numerical relativity code, if we throw more and more computers at it, the performance doesn't strictly always improve, right? In fact, after a few hundred to maybe several hundred cores have been put on a single problem, the performance pretty much plateaus. So this is the scaling that current codes approximately display. Whereas Spectre, because of task-based parallelism and everything else, is able to scale quite well, all the way up to 500,000 cores that we were able to use on the Blue Water supercomputer in the US. And it scales linearly, which is very good, which is exactly as we want. And this demonstrates especially the power of task-based parallelism that we use. And this makes Spectre future-proof because, as we are seeing, it's not that individual computers are becoming faster. We are simply getting a lot more of those cores on each chip, right? Okay, I am going to skip this part and summarize here. Okay. So in summary, currently we are developing a code called Spectre, which is a radically forward-looking computational astrophysics code. While it is currently being designed specifically for numerical relativity, it can be quite easily used to solve fluid dynamics and other problems. And it has been open source since a long time. It's available on GitHub. You can just go to github.com/sxs-collaboration/Spectre. This is a snapshot of its webpage. And the three key new paradigms that it uses are DG discretization, discontinuous Galerkin discretization, local time stepping, and task-based parallelism. Okay. And the use of task-based parallelism will enable the successful use of future exascale computing that we are heading toward. Currently, Einstein's equations, GR-MHD equations have been implemented. Domains are constructed. We are able to approximately do mesh refinement. The treatment of the boundaries is complete. People are working on having the control systems work properly. And this is where we are at. So this is where I'll stop and take further questions. Thank you so much.
So thanks, Prayush, for a wonderful talk. And now the floor is open for questions, so you can unmute yourself and ask any questions that you have.
Recording stopped.
So yes, you can please go ahead and ask questions.
I have a question.
Sure.
Okay, so when we are performing test of GR using this waveform matching, we basically assume that Einstein's gravity is true, but have similar waveforms been generated for modern gravities theories and compared to what we are getting from the data?
Right, that's an excellent question. So the short answer is no, and the long answer is no, because it's extremely hard. And however, it's not a lot of people have been thinking in this direction, and people have done simulations, I think, in DCS in a perturbative manner, where you have scalar field coupled with the usual Ricci scalar and so on, and they take a perturbative limit of that in a way that the zeroth order solution is simply the Einstein's equation solution. And on top of that, they evolve the coupled scalar field. And using that evolved coupled scalar field, they calculate the first order solution for the metric. But while it is done entirely numerically, it's not numerical relativity in its true sense, where we don't make approximations. And this this is fundamentally because it is for every theory you want to solve for, you must be able to construct initial data, you must be able to construct a Cauchy problem for it, and so on. And that part requires some years of mathematical work before it can be actually applied in numerical relativity. So yes, this is actually an exciting direction. People are thinking about it. If you're interested, then we should talk about it.
Yeah, thank you. So but that makes me just wonder that when these papers are writing that they're performing test of GR and then no deviations from it, but it could happen that we have a black hole in a modified gravity setting, which can exactly fit the parameters that we are detecting. Mass acceleration plus rotation plus some hair will give a better match to what we have detected.
Right.
Does that make sense? Yeah. So that's what I'm saying. That how can we say that we are actually testing GR then using these waveforms? I mean, there's still a huge open field out there. Like, for example, the first gravity.
That's right.
Yeah.
So you're right in some senses. In the sense, first of all, the way tests of gravities work is they look for deviations from GR. Yes, they're not looking for agreement with a specific non-beyond GR theory. They're looking for any deviations from GR predictions. So in order to look for those deviations, we must have a very, very solid understanding of what GR actually predicts. And that's where numerical relativity currently comes in, to give us an absolute unprecedented precision on what GR predictions will look like. Now, that is required to measure anything that we present in your data that is not modeled by the model that you're using. Your question is, what happens if we have some theory where you can, the solution space in the theory for the binary problem is degenerate with GR, in the sense that you can change some parameters of the black holes, and in that alternate theory come up with the same waveform as you would in GR with a slightly different value of black hole masses and spins and so on and so forth.
Yeah.
And that is possible, and I'm not sure how exactly for a single signal one would be able to tell one from the other, but one could think of a way for a collection, to use a collection of signals to sort of make a statement, right?
Yeah.
However, this is a question that is not touched upon in my talk at all. So this is a question about can we test GR, and a lot is open in this field. Definitely, there's definitely scope for future work in numerical relativity, beyond in theories beyond general relativity. That is absolutely true. Yeah, but it's not that the current tests of GR are wrong. It's just that they're looking for deviations. They're not looking for agreement with another theory. They're looking for deviations from current theory. And I'm always rooting for successful violations of GR to be observed. So it's not very heartening that most of the times these null tests come up with basically a null result. So we have not been able to find any genuine deviations from GR predictions yet.
Okay, thank you. Yeah. Maybe I will write to you if I have some more questions.
Yeah, absolutely. Please feel free to write to me about this, any other question, and if you want to know and use Spectre and so on and so forth.
Thank you.
So I see more hands up. I think Shailesh.
Yes. Go ahead.
Hi. So hi. Am I audible?
Yeah.
Yeah. So I have a question in the similar line, actually a bit different from the context of the talk you presented. It's a very nice talk, actually. So thanks. So the question is actually what are the key limitations in current binary black hole waveform models, actually? So particularly concerning about this eccentricity and higher order multiple moments. So can you a bit comment or discuss about it?
Right. So key limitations as I see them in current black hole waveform models is in handling high mass ratios. So the hard problem is, how do we model high mass ratio systems on both circular orbits and eccentric orbits? So let me answer it from an opposite point of view. What we have very good models for are quasi-circular binaries with or without spinning black holes. That we can model quite well. Yeah. But anytime you introduce, for example, eccentricity, it's unclear how accurate a waveform models are. If you include spins precession in addition to eccentricity, then we don't really have very good models beyond perturbation theory, like post-Newtonian theory models.
Yes, yeah.
So that is one direction. And the other direction is of mass ratio. Now, even for quasi-circular systems, eccentric systems, for high mass ratios, we have very little information from numerical relativity, and self-force information may or may not be sufficient. Post-Newtonian theory is definitely not sufficient. So mass ratios of 50 and higher is where we have basically no information from anything. So all we are doing is extrapolating from everywhere and constructing approximate models. So high mass ratios is one of those frontiers that we must break through, and eccentricity plus precession is another frontier that we must break through.
I see. So yeah, so you mean like even in the small mass ratios, including the eccentricity, you still have some limitations or causing problem modeling the waveforms, right? Even with the
with
small
or without
mass
eccentricity. With or without eccentricity.
Okay, I see. Okay, I see.
Right.
Yeah, thanks.
Hey, I mean, promising work is happening in the self-force community, but
yeah, that's
restricted to non-spinning black holes there. And in nature, it's quite unlikely we'll have non-spinning black holes.
Right, that's right. Yeah, thanks very much.
You can take one more question, given the time constraint. So go ahead. I can see one raised hand. So
Salman, maybe you want to ask a question?
Yes, sir. I am asking you, sir. Is there any or online resources from there we can know or learn the gravitational data analysis or this use of these softwares like
So if you go to YouTube and go to the, let me open this right now. If you go to the ICTS page of YouTube, International Center for Theoretical Sciences, we conduct a lot of conferences and schools and programs. That includes every year, we have gravitational wave schools that happens in the summer. And all the lectures from that school are uploaded to this channel on YouTube. I'm sure you can see my screen still, right? So if you just browse through this channel, you'll find lots of lectures on gravitational waves. On both gravitational wave astrophysics, data analysis, and numerical relativity.
Okay. Thank you, sir.
Any more questions? Quick questions.
So Sayantan has raised his hand, so you may take up his question.
But the hand is raised for a long time.
No. Actually, I know the time is constant, so I'll just ask a very short question. Actually, so you actually did two time splitting, right? In 53 pages, like in 1:60 ratio. So I'm just asking that what is the radius you take the tolerance, right? Is it where the post-Newtonian is valid or what? Like at what range you define that? I mean, outside the time scale is the normal one, and below we need to take the small grid. So is there this one? So could you just tell what level you take the time slicing, like you take this one, and whether it is the post-Newtonian limit or like what? So that is my question.
So I see the question, but I'm a little confused by the word phrasing of the question. You asked what level do I take the time slicing? Yeah. It's not the time slicings are not different. Slicing is exactly the same. We have the same lapse and shift, which induce the slicing. So lap field and the shift vectors, they're vector field. They're all the same everywhere as before. The only difference is how large time steps we take in different parts of this whole domain, right?
Yes.
And
so what is the radius
yes.
of influence you take the times, time steps? I mean, that's what I'm saying.
Right. So the exact radius, I forget. It will depend on the relative size of the two horizons. It depends on the relative size of the two black holes, typically. And for some radius around the smaller black hole, we take the smallest time steps. And
so is it the dynamical horizon or what?
Describe some. So these are dynamical horizons, yes.
Okay.
No, my point is that this radius where we take small time steps, it's not. So the question is about how wide is this box in which I'm taking small time steps, and how wide is this box where we're taking larger time steps, and how do I know how to keep this wide and so on. The answer is not coming from post-Newtonian theory. The answer is coming from practical measurements of error. We try to make this as narrow as possible. We try to take small time steps as locally as possible. That gives us errors in our solutions. We measure those errors, then we go back and we increase the region where we take a small time step. And we iteratively figure out, okay, this is a stable region where we can get away with time steps of this particular size. And this is another region where we can get away with time steps of twice the size. So it's determined dynamically based on the error estimates of the solution. It's not on some a priori theoretical prescription that we start with.
Okay, thank you.
Does that make sense? It's much like adaptive mesh refinement, right? Our meshes are also adaptively refining based on dynamically measuring errors in our solutions. It's the same thing, only in the time dimension.
I was just thinking that whether it is a theoretical cutoff or not. I mean, that's what you were saying. Okay.
Theoretical cutoff. Cutoff is a very strong word. There's no strong requirement where we should have a cutoff. The real difficulty is how well we are able to extrapolate forward in time. So now let's take, for example, this time step. Yes, from going from this to the next time step, we need information from both neighbors. From the right neighbor, we have information, but from the left neighbor, we have no information. So we need to extrapolate forward in time in this neighbor to sort of construct approximate values of the metric and all the fields here. And that information we take here, and that is how we are able to evolve from here to the next time step, right? So this extrapolation that we are doing forward in time here is what really is the key source of error, obviously. And we keep monitoring that error, and depending on how large or small it is, we change the size of this region.
Thank you.
I think the time schedule we can conclude here. We thank Prayush again for excellent.
So
and if you have anyone has other questions, please feel free to reach to him directly. So we thanks Prayush, and I will hand over to Srijit for the next session.
Yeah, thanks Arpan, and thanks Prayush for a very nice talk. So just a quick query. I mean, would it be okay to share these slides with the participants, Prayush?
Yes.
Yeah. Okay. Thanks. So thank you again, the speaker of day 2, the first session, Prayush Kumar from ICTS, and thank you, Arpan, for chairing this session. So now I would like to invite Dr. Devaprasad Maiti from IIT Guwahati to chair the sessions, remaining sessions for day 2 till this afternoon break. Devaprasad Maiti is a faculty member at the Department of Physics, IIT Guwahati. His areas of interest are gravity, black holes, extra-dimensional scenario, and cosmology. So over to you, Devuda. You are muted. Please unmute.
Okay. Thanks, Srijit. Yeah. So, am I visible? Can you see me?
Yes.
My video is on. Okay. thanks, Srijit, for this nice conference, online conference.
Amitabh is also around, I hope so.
Amitabh is around?
Yes, I am around.
Yeah.
Okay, so can you please share first? It would be better if you can share with them.
Yeah, somebody has to allow me to share. So
okay, Srijit.
Yeah, okay. So now I am a co-host. So indeed, no. Okay, so can you see my screen now?
Yes, Amitabh. Yeah, I can see. Okay. So, so before the break, we'll have two talks. Both the talks are essentially the continuation of the talks that had been given in the previous day. So, without any no introduction, I think so everybody knows Amitabh Virmani. So let me start. Amitabh. So he'll be talking about basically the continuation of the earlier talk on Bondi-Sachs formalism. So over to you, Amitabh.
Okay, thanks, Srijit. Thanks, Prasad.
Recording in progress.
Yeah, so actually before I start, let me, because some students were asking me about references and so on. So before I give the outline of my lecture, let me say two references. So there is a very nice review by Compare and his student Firucci. It appeared in 2018. And now published in Lecture Notes in Physics in this volume. So chapter 3 of this review has very good discussion of null infinity and basics of Bondi-Sachs formalism. And there is a more detailed review which talks about connection to conformal infinity and various other approaches. This is by Jeffrey Winokur and Thomas Madler. They are both very well-known people in this subject. This review came out in 2016 and is published in this Scholarpedia. Okay, so here is the outline of my second lecture. I will review a few things I said yesterday. So I will start by a discussion of gravity in Bondi gauge. Then the mass aspect I have already discussed. Today I will discuss the angular momentum aspect. And I will combine this discussion with the equation of motion analysis. So, because many of you were asking yesterday about the equations of motion, so I will combine the two things in a right set of ways so that you see how the equation of motion analysis works and how these functions come out. Okay, so this will be the end of the sort of the elementary Bondi-Sachs formalism in a way. Like I am after the first part, I am done with the radial direction. Then I will discuss boundary conditions in the U direction. Okay, so this is the thing which are sort of more modern, and these are the things which people are discussing these days. Then I will discuss asymptotic symmetries, super translations, and Lorentz symmetries is what I will focus on. And finally, I will discuss modern topics that people are discussing on the archive. In particular, Bondi-Sachs formalism in De Sitter is one such topics. Then I will end with my conclusions. Okay, so is everything okay? People can hear me properly?
Yes, I think we can. Yeah, go ahead.
Okay, great. Okay, so let me start with where I sort of ended yesterday. This was the last set of slides I had in the previous lecture. So I said that when we write the metric in Bondi gauge, we are using u, r, theta, phi coordinates, and we use 4 gauge conditions. 3 of these gauge conditions are these. So GRR is 0 and GRAA equal to 0. Okay, and the determinant of the sphere part of the metric is said to be r squared times some function of theta and phi. So these 4 conditions completely gauge fix the metric. And if you can bring a metric into this form everywhere in your space-time, then you are in Bondi gauge. Okay, everywhere. But many people were asking, is it easy or is it difficult to bring this? It's very difficult to bring a given arbitrary metric into this gauge. Even for curve solution, if you try, this is a lot of work. Although it has been done, but for curve solution, this is a lot of work. Okay, so, but this is just a gauge choice. You can do this not for curve solution, you can do it for any solution. You can take curve anti-De Sitter, curve De Sitter, whatever solution you want, you can try to bring this in this gauge. But now on top of that, we want to use some properties of Einstein's equations and some physics inputs. So we say that I'm interested in studying asymptotic flatness in Bondi gauge. Okay, so I'm looking at asymptotically flat spacetimes in Bondi gauge. Now, Minkowski space in Bondi gauge has this property that GUU is -1, GUR is -1, GUA. There are no cross terms between angles and the U coordinates. So GUA is 0 and GAB is R squared times the round metric on the sphere. So this gamma AB is the round metric on the sphere. So this is the right hand side of these equations. These are the components of the metric components of the Minkowski metric in Bondi gauge. So now we expect the asymptotic flatness definition to be something of this type, that when we take the limit r going to infinity, this should become -1, this should become -1, this should become 0, and this should become r squared times gamma AB. So this is our naive expectation. And yesterday there was a lot of discussion on this point. A detailed analysis, which was not done over one night. This analysis was done over many papers and it took many years. There are like 13 papers that Bondi and co-authors wrote in order to sort of finalize this sort of discussion. So a detailed analysis shows that these are the correct boundary conditions to use. So UU component should be -1 plus something which corrects the metric at order 1 over R. So this is capital O, order 1 over R. GUR doesn't have 1 over R component. GUR has 1 over R squared component. GUA has order R to the 0 component. Okay, this might be a bit different from what your expectation is, but this is the correct thing to do. If you don't do this, then there are other problems. So this is the correct thing to do. And GAB is indeed R squared gamma AB plus some correction of order R. Okay, so now this is what I wrote in the previous lecture. In our previous lecture, we wrote that the Minkowski metric is this, and then in Bondi gauge, these are the correction to leading order. So there is 2m over R du squared, then R times CAB dxa dxb, and then this is this cross term, GUA term. This comes because of the equation of motion analysis. You don't have a choice, because if you want CAB to be non-zero, then this must also be non-zero. Divergence of CAB du dxa. Okay, and today's lecture will be about the dots. We are discussing the subleading terms in the expansion. Okay, but before we go into the subleading terms, if you want to get something out of these lectures, then CAB is the most important quantity. CAB is the quantity that carries every information about gravitational waves in this Bondi-Sachs formalism. The U derivative of CAB is the news. It has 3 names, news tensor, Bondi news, or Bondi news tensors, whichever you call it. So I just call it Bondi news tensor. It's the longest possible name you can get. Bondi news tensor. This contains information about what happened in the space-time dynamically. So at null infinity, NAB contains information about flux of gravitational wave, energy of gravitational wave, angular momentum carried by a gravitational wave. All of this is in this NAB, which is essentially in CAB. Okay, so the second most important quantity is this function M. This is a function of U and the theta and phi. So the notation is XA is theta and phi. This is called the Bondi mass aspect, or simply the mass aspect. What this is telling you is how much mass is in different directions of your spacetime. The integral of this function will give you the Bondi mass. And since many of you were asking about the equations of motion analysis, before I introduce the angular momentum aspect, let me say a few things about the angular momentum, about the equations of motion analysis. So let me say a few things about this before going further. Okay, so the way we do this, so the basic idea is that we analyze Einstein's equation in a very specific order. If we analyze the Einstein's equation in this particular order, then the analysis becomes sequential. You solve first equation, then you solve the next equation, you solve the third equation, and so on. And if you do this in this order, the things are very simple. But if you just enter into Mathematica and find the total Einstein tensor, it will look completely hopeless, and it will not be clear how to even go about analyzing that expression. Okay, so this was all done by Bondi and collaborator, and later improved by other people. This discussion in particular was improved by Vinicure in one of his later papers. Okay, so here is the summary. So what we look at is, instead of looking at the Ricci tensor equal to 0, we look at the Einstein tensor equal to 0. So GAB, RAB minus half GABR. The first constraint is the radial constraint, GRR equal to 0. So when you put GRR equal to 0, you will get an equation with derivatives containing R. Those derivatives, if you try to do the expansion of various quantities, beta, V, UA, these are the functions I introduced yesterday. If you do the expansion for those functions, this equation will fix your beta in expansions in powers of 1 over R. Similarly, if you look at the cross constraints, GRA equal to 0, these equations will fix your UA. So I will give examples of both these in the next slide. If you look at the UR equation, this equation fixes V. So of course, as you can see, I mean, this is impossible to remember, but you look at a paper, and the key point I want to emphasize is that there is a sequence, there is a specific sequence in which you have to do this analysis. If you do the analysis in this order, then things are quite manageable and quite simple. Now, once you have GUR equation fixed, it's very interesting to see that GUR equation is same as analyzing the trace of R equal to 0. And the way this comes about is quite interesting. So it comes about like this. So GUR is Ricci tensor UR minus half of the UR component of the metric times the Ricci scalar. Now look at the Ricci scalar. So Ricci scalar in Bondi gauge is UR. This is the contraction that will appear, and RR contraction will appear, and RA contraction will appear. Okay, but these are the two equations that we have analyzed in our step 1 and step 2. So these were these equations, GRR and GRA. So if you use those equations, then you see this is just UR and RAB. Okay, but since we are interested in studying UR equation, everything is equal to 0. So this is essentially the same as studying equation with the GAB RAB equal to 0. So this step 3 is same as GAB RAB equal to 0. So the key point I wanted to emphasize by this little discussion is that as you do expansions of Einstein's equations, there are many such identities that one may need to use. So it may happen that the third order expansion of this equation is closely related to the second order or third order expansion of this equation, and so on. So there are close relations between these various expansions, and these expansions one has to keep using in order to simplify the analysis. Okay, so now moving further. So if you want to analyze the other equations, let's say GAB equal to 0, then this GAB equation, it is best to split into the trace and the trace-free part. So the trace-free part is this, and the trace part is this, and the trace-free part is this. Okay, so now I'm not going through this analysis, but again, a simple analysis shows that these equations are automatically solved due to Bianchi identities of the Riemann tensor. So one doesn't need to solve these equations essentially. So we can skip the step 4 and we call it step 4 prime. So now you see what has happened. So out of 10 Einstein's equations, we have already solved these many of them. So the RR equation we have solved, RA equation we have solved. So RR equation fixed beta, RA equation fixed UA, RU equation fixed V, and AB equation did not fix anything. They are just automatically satisfied. Now there are 2 equations left. Let us do the counting. So 1 equation here, 2 equations here, 1 equation here, and 3 equations here. So 3 plus 1, 4, plus 2, 6, plus 1, 7. So seven equations we have analyzed, only 3 are left. And those 3 equations are UU and UA. Okay, so I call this logic to be step 4 prime. And then the UU equation will tell you how the Bondi mass aspect is evolving. So this is the equation that will tell you how the Bondi mass is changing in your space-time. And UA equation will tell you how the angular momentum aspect is changing in your space-time. Okay, so now I will define what this angular momentum aspect is, but I gave an overall picture of how these equations get organized. So if you analyze this in this order, then first you solve for beta, then you solve for UA, then you solve for V, and then you solve for the MU dot, M dot, and finally for the NA dot. This is the logic. So if you analyze the equation in this specific order, the analysis is very manageable. I will come to the angular momentum aspect in a moment, just to give an example. Okay, so here is an example. So if you analyze the first equation and do the expansion of this function beta in powers of 1 over r, then asymptotic flatness requires beta 0 to be 0. Einstein's equations will tell you that beta 1 is 0. Then beta 2, Einstein's equations will tell you, is related to the CAB, the quantity that determines the Bondi news in this way, minus 1 over 32 CAB. Okay, so like this is how it happens. So now let's look at another example. So this is UA equation. So UA has an expansion in powers of 1 over r. So this is the 0th component, then the first component, the second component, second component meaning in powers of 1 over r. The asymptotic flatness requires the UA0 to be 0. If you analyze Einstein's equations, you will see that UA1 turns out to be 0. UA2 turns out to be divergence of CAB. This is what I said in the previous lecture, one of the earlier slides here. You see, when I was saying that the cross term is divergence of CAB, this is that equation. The minus signs are there because the U has a minus sign. And then if you analyze the next order equation, you get an arbitrary function, exactly like you got the arbitrary function in the expansion of V. So here you get an arbitrary set of functions. These are called NA. So U3A has NA and then some other term which is related to the C field. So NA are the integration constants in R, but they are functions of U and X. And this is called the angular momentum aspect. Okay, so these are the four physical quantities in Bondi expansion. So one is CAB. CAB is the thing that carries information about the gravitational waves. M is the Bondi mass, which contains information about the mass of your space-time. And NA is the information about angular momentum aspect of angular momentum of space-time. So there are two components, n theta, n phi. Okay. Similarly, the V equation has this kind of expansion, minus 1 plus 2m over r. M is the Bondi mass, which I discussed earlier. Okay, so now finally we are left with three equations because all the expansions are solved, all the arbitrary functions are obtained. Now the last step will give you the evolution equations for the Bondi mass and angular momentum aspect. So finally we have the equations for the evolution of the mass and the angular momentum aspect. So del U of M equal to something and del U of NA equal to something. This is where all the physics of, most of the physics of Einstein's equations are. These are the evolution in time. These are the, okay, so in asymptotically flat spacetimes in vacuum gravity, these equations are not very difficult to write. I can write them in just 2 lines. So the equation tells us that del U of M is a double derivative of the News tensor. And here the derivative of the angular momentum aspect is related to some sort of double derivative of this C function, the C tensor. A C tensor doesn't have a name. It's perhaps the most important quantity, but doesn't have a name. The N tensor has a name, Bondi news, but C doesn't have a common name. Okay, so why the name angular momentum aspect? The name angular momentum aspect because it is closely related to the angular density of the angular momentum with respect to the origin defined by the Bondi coordinates. So Bondi coordinates naturally define some origin r equal to 0. With respect to that origin, the space-time carries angular momentum, and the integral of n will tell you what is the angular momentum. Okay. So now there is a lot of discussion about what is the meaning of angular momentum, and there are many papers on this. I will not go. This is not the place to go into those details. This is a pedagogical lecture. So let me just say that, roughly speaking, if you just do the integral of n lower component phi over the angles, then you will get your the total angular momentum of the spacetime. Okay, so for the experts, like this is not the correct formula. There are other terms in the formula, and there is a lot of discussion about those other terms in the formula. But I think if you are seeing this for the first time, then I think this is good enough, that you take the angular momentum aspect and do the integral over the sphere, you will get the angular momentum of the space-time. Okay, so let me make a summary of all this. This might be a bit technical for people who have not seen this, or maybe technical for people who are not interested in this, but let me just make a summary. So as you can see, this part of the analysis is tedious, lot of calculations are required. But the key point that I wanted to say, and this is what I emphasized in my previous lecture also, the whole analysis is very hands-on. You can give it to a student, and student can program these things and compute all the equations in powers of 1 over r expansion. Okay, there is no fancy mathematics involved. There is no difficult differential geometry. It's just covariant derivatives you write in terms of the sphere derivatives. It's just very long and tedious calculations. There is no, in my opinion, there is no very fancy math and no difficult differential geometry. So as far as the expansion in powers of r is concerned, once you put things in Bondi gauge, you make some choices about how to expand these things. You can just do these calculations. Okay, so this is one of the main message I wanted to give from my lectures. Okay, so this is all I wanted to say about the radial expansion. Now I will go into more detailed discussions of other things. Yeah, so this is a good place to stop for me to take questions. Actually, this is the part that I really wanted to convey from my lectures. So if people have questions, comments on this point, I will be happy to take now.
So if you have questions, please unmute yourself and ask.
Okay.
Okay, so there is one question in the chat box. Maybe I can repeat.
Yeah.
So, I mean, I'm not sure. Okay, Sayantan Ghosh, are you there? Can you please just ask it? Sayantan? So I'm not understanding his question. Sorry, my mic. Okay, his mic is not working. So his question is something easy like the
Kumar integral in the ADM formulation. Yeah.
Yes.
Yeah. So in fact, so this is something I discussed briefly in yesterday's lecture, but I will discuss more in the today's lecture. In the u going to minus infinity, the angular momentum expression will indeed become the ADM angular momentum. And as you said, the ADM angular momentum is closely related to Kumar integral. So indeed, one can make all these connections. Yeah. But this is only in the u going to minus infinity limit. Okay, thank you. Yeah, okay.
Okay, so is there any other questions? Okay, maybe you can continue, Amitabh.
Okay, thank you, Prasad. Okay, so now, so this is all I wanted to say about the basics of Bondi-Sachs. Now I'm moving into more research directions. Okay, so boundary conditions in the U direction. So this is one topic which is much discussed in the literature over the last few years. Okay, so physically, what is happening? So let us consider a class of spacetimes where the solution starts from flat space in the far past and goes back to flat space in the far future. Okay, so this is a situation. You have Minkowski space far in the past. So m, the Bondi mass in the v going to minus infinity limit is 0. Then some sort of gravitational wave comes. Maybe the space-time has some mass, and then this gravitational wave scatters and goes to infinity. Okay, so this goes to infinity. So in the end, m at u going to plus infinity is also 0. So in between there is a mass. So here the mass is 0, here the mass is 0, but in between there is some mass here, there is some mass here. The mass is changing as a function of v, as a function of u, and so on. Okay, so these classes of spacetimes, so consider all such spacetimes which are possible. These classes of spacetimes have been favorite for mathematical minded relativists, and they can be dealt in a very rigorous way. These are called Christodoulou-Clairamin spacetimes. Okay, so these are very popular in mathematical GR literature, and you will see why they are popular in the physics literature in a moment, just 3 lines below. So a study of these spacetimes reveal that the following boundary conditions in U are satisfied by this class of spacetime. Okay, so this is the analysis done by these mathematicians. What they have shown is that the Nu's tensor falls off like 1 over U. Any power higher than 1 over U, as you go, U going to plus minus infinity. So that is to say, as you approach this spatial infinity point, that is the case when U is minus infinity, and as you approach here, U going to plus infinity. In all such situations, in both these situations, in fact is true for the past also, in all such situations, the Nu's tensor falls off as 1 over U, a power higher than 1 over U, such that this space-time has asymptotic flatness in the past and asymptotic flatness in the future, and I mean they remain Minkowski-like everywhere. Okay, not only the NAB falls off like this, the Bondi mass function, the M and NA remain finite everywhere. So M and NA have finite limits as U goes to plus minus infinity. So there can be some mass in this spacetime. So the ADM mass of this spacetime can be non-zero. So they may have some ADM mass, but the amount of, since the Nu's tensor tells us about how much energy the gravitational waves are carrying. So the amount of energy gravitational wave carries in this very little region near spatial infinity, that is very small. In fact, 0 in the U going to plus minus infinity.
Okay, Amitabh, just because it's the question that somebody asked written in the chat box, the question is relevant at this point. That is why I just interrupted you. Sorry for this.
Yeah.
So the question is, because your gravitational wave going in and then scattered going to the infinity. So question is, I did not get what happened with that mass, because mass is equal to energy. So that was the question. If you look at the chat box.
Yeah. No. So of course, the mass is equal to energy. I mean, but the mass can be carried by different type of particles. Mass can be carried by. Okay, first one has to make a distinction between the ADM mass and the Bondi mass. ADM mass is the mass that tells you about the total mass of the space-time, like the gravitational waves in the space-time, the black hole in the space-time, stars, all those things are captured by the ADM mass. The Bondi mass is telling you the dynamical mass of the space-time. As the space-time is evolving, some gravitational wave is coming out. So it is telling you how much gravitational wave has come out in a way. So like if you calculate this is something I discussed yesterday. So if you calculate mass at point U2, then mass at point U2 is mass at point U1 plus the amount of flux of gravitational waves that has come out. Okay, so the mass is equal to energy. That statement is true. But okay, now there is one more technical question. What is the distinction between Misner-Sharp mass and ADM mass? Okay, let me first make a general comment. So the general comment is that there are many definitions of mass in general relativity. There is a canonical definition which is based on the Hamiltonian methods. So the generator of time translation defines a notion of a Hamiltonian, and that Hamiltonian defines a notion of mass. So that is called the ADM mass. The Misner-Sharp mass, I do not know exactly what the definition is, but in situations where this mass can be compared to ADM mass, I would think that this agrees with the ADM mass. I mean, there are hundreds of definitions of mass in general relativity. There is no end to this. Kumar mass, Ashtikar-Hansen. I mean, there are many definitions. So, but there is a canonical definition which is the generator conjugate to time translation, and that's what we mean by the ADM mass. And I'm quite sure that this Misner-Sharp mass, most likely it corresponds to the spherically symmetric setup with dust or something like this. I have seen this definition somewhere. But in the context of our situations, it will be equal to the ADM mass. Okay, so are there other questions?
No, I think there is no other. So you can just let me see.
Yeah.
Yeah, go ahead. Yes.
Okay. Okay, so this was the work of these mathematicians. They are very famous mathematicians, but now physicists have to do something more. So what we do is that we just jump. So physics jump. Okay, so this may be a wild jump. Mathematicians may not like it. Okay, but that's fine. So what we do is that we do not expect this fall off to change even in the black hole spacetimes. Okay, one can debate whether this is true, not true, correct, not correct, whatever. But this is the jump that we make, and then we try to make some progress. So that is to say, we expect these boundary conditions to be good boundary conditions even when the black hole forms in the spacetime. Okay, so with these boundary conditions, with these assumptions, one can do a number of things. So here is an example. So since the Christodoulou-Clairamin spacetime have this property that the Bondi news goes to 0 as u goes to minus infinity, we just put this in this equation and we observe that del u of m goes to 0 as u goes to minus infinity. Okay, that is to say the mass of the spacetime becomes constant as u goes to minus infinity. Okay, so the mass of the spacetime has become constant in this limit. Similarly, from the other side, the mass of the spacetime will become constant from past null infinity. And then one can ask whether the mass defined at past null infinity matches with the mass defined at future null infinity. Okay, so this is some question one can ask. And this is one question that has attracted a lot of attention. And people have tried to use matching of physics at past null infinity to physics at future null infinity. Okay, and this is based on this physics, essentially based on this physics jump, which takes these boundary conditions even for black hole spacetimes. Okay, so I will give you another example. So another example is this. So I said that the angular momentum aspect, the u derivative of the angular momentum aspect is given by this function. Now, if one do the analysis for Christodoulou-Clairamin spacetimes and assuming this physics jump, then a separate analysis shows that del u of NA also goes to 0. Okay, this argument is different from this argument, but a separate argument shows that like the del u m goes to 0, del u of NA also goes to 0. That is to say the angular momentum aspect becomes constant in u as you approach u equal to minus infinity. Now, this would imply that the right-hand side of this equation becomes 0. So you see, this is a condition on the C function now. So if this quantity becomes 0 at u going to minus infinity, then you can say something about the C function, the C tensor. And remarkably, it turns out that if this equation is satisfied, the C function is specified by a scalar function. The C tensor is specified by a scalar function now. So this equation implies that the CAB is derivatives of a scalar function C and some Laplacian acting on the function C. Okay, so C is a scalar function on the sphere. So as a result, what has happened is that given this physics jump, what has happened is that on the null infinity, there is this new tensor NAB, and at the place where it meets spatial infinity, you have these three quantities now. So you have m, the Bondi mass aspect, which has no dependence on u anymore because you are at u equal to minus infinity. The n only has dependence on the coordinates, u dependence has gone. And because of these u dependence being gone, the CAB tensor has reduced to just one function C, okay, which is defined at the past of the future null infinity. Okay, the same is true for the other side. Okay, so this is the future null infinity. The same is true for the past infinity. So scribe plus, you have these three functions now. Four functions, and at scribe minus, you have these functions: C of xa, m of xa, na of xa. So a key question that has attracted a lot of interest in the last 10 years is the relation between these quantities. What is the relation between the C function at past null infinity, the future of the past null infinity to the C function at the past of the future null infinity. The relation between C function at this point to the C function at this point, the mass functions and so on. Okay, so this relation has been explored through spatial infinity, and many papers have come out on this subject. Okay, so now this is all I wanted to say about the boundary conditions in the U direction. I am happy to take some questions here. Yeah, so Indranil has a question. What happens when you couple matter? Is there a similar fall off like Bondi news? Yeah, indeed, one can do this analysis with matter coupled. In the references I mentioned, there are comments, and then from the references you can find the papers. With matters, the analysis is much more detailed. As I was saying in the previous lecture, there is this art and science balance. So what kind of boundary condition you want to allow for the matter, this will change the boundary condition for the metric, and then you have to find the right balance. So there is a lot of richness that one can explore. Okay, very good. How I am doing in time? I have only 20 minutes or so left. Okay, so let me continue. It doesn't matter how much it doesn't matter if I finish my lecture or not. I will just say a few things and then stop. Okay, so the next topic I want to discuss is asymptotic symmetries. So what do we mean by asymptotic symmetries? So asymptotic symmetries have some complicated definition, you can say, like it has some definition in terms of Hamiltonian charges and so on. We will come to that in a moment. We are asking a simpler question. What we ask is, what are the vector fields that preserves the Bondi gauge and the boundary conditions that we impose? Okay, so try to understand the question. So we have metric written in Bondi gauge, and we have imposed some boundary conditions on the metric based on some physics inputs. Like we want to allow for gravitational waves, we want to study the energy of these waves, the energies should be finite and so on. So we have put some boundary conditions on our fall-offs. And now we are asking the question, what are the vector fields that preserve this Bondi gauge and the boundary conditions? Okay, so let us just make them equations now. So the Bondi gauge is GRR equal to 0. So I want to look for vector fields such that the Lie derivative along those vector field of the GRR component is 0. So similarly, GRA is 0. So Lie derivative of GRA along that vector field should be 0. And the radial coordinate has to satisfy this determinant condition. The determinant of G, this is the metric on the sphere. So determinant of the metric of the sphere divided by R squared is only a function of theta. So I can write it like del R of this quantity is 0. So the Lie derivative of del R of this quantity must be 0. So these are the three conditions which are sort of just preserving the Bondi gauge. Okay, so now we have the boundary conditions also. So the boundary conditions were GUU falls off like 1 over R. So the vector field should be such that the Lie derivative of GUU should also be 1 over R. Okay, otherwise the boundary conditions will change. So we don't want that to happen. So the vector field should be such that they should preserve the boundary conditions. So GUU must be, or Lie derivative of GUU must be 1 over R. Okay, similarly for the other cases. So the UR falls off like 1 over R squared. So the Lie derivative of UR should be 1 over R squared. Lie derivative of UA should be R to the 0. And Lie derivative of GAB should be R to the 1. The third condition you don't have to write in a covariant form. This is a scalar quantity. Lie derivative on the scalar quantity is just xi mu del mu. So you don't have to write it in a covariant form. This is a scalar quantity, is a covariant quantity. Yeah. Okay. So now this is a bit of a jump. I cannot explain this in real time. So you see, so you have a lot of equations now. So you have this Lie derivative equations. So 4 equations coming, number of equations coming from here, number of equations coming from here. You can write all these equations in partial derivatives and analyze them. It will take you maybe 2 hours or 3 hours to analyze what are the conditions all these equations are imposing. But believe me, this is not a difficult exercise. You just write all these equations and analyze which component of which vector should be what and so on. If you do that analysis, a calculation will show that the following vectors preserve the Bondi form and the fall off. The following vectors preserve the Bondi gauge and the boundary conditions. So let me explain what these vectors are. So these vectors depend on two functions. So one function is capital T and the other function is a vector actually. The other is a capital vector R. So RA. The U component of this vector, the partial U, the U component of this vector depends on the functions like this function T appears and the derivative of this R appears. Okay, and then there are corrections. Corrections are to order R to the 0. Okay, this is the little O notation which I reviewed in the previous lecture. That is to say, the corrections start with at least 1 power of R. 0 power of R because R to the 0. Okay. Then the angular part is RA. So you see, so the way these functions are defined or designed are precisely this, that the U component should be T times del U and the angular component should be RA times del A. And then there are corrections. So 1 over R DAT, this correction is coming because of the T. And the R component of the vector has various things which are constructed out of derivatives of the functions T and the vectors R. The key point, the details are not so important. I mean, once you understand what this is, you can substitute this in Mathematica and check whether the boundary conditions are satisfied, gauge conditions are satisfied. So checking this is also not very difficult. Easier than finding them, but finding them is also not very difficult because there are many equations you have. So all these equations you just analyze in some organized way and you will get this answer. Okay, the key point is that there are arbitrary function, at least one arbitrary function that appears in this analysis, and this is called the supertranslation. So T of XA is an arbitrary function which appears in this analysis. This is called the supertranslation. The name supertranslation, we will explain why this is called supertranslation. The other function that appears is this vector, the vector that appears is this RA. So this is a vector on the sphere. And this vector obeys conformal Killing equation on the two-dimensional sphere. So dARB plus dBRA is gamma AB dCRC. Okay, so if you restrict yourself to smooth vector fields, okay, this is what I will do in this lecture. If you restrict yourself to smooth vector fields, then these R's are the Lorentz generator. So there are 3 rotation killing vectors and 3 boost conformal killing vectors. So 3 plus 3, 3 rotations, 3 boost, and they form the 6 generators of Lorentz group. And they are all solutions to this equation. On the sphere, they are the solutions to this equation. Now, to simplify our life, we consider R equal to 0. Okay, we are not doing any rotations or any boost. So just putting T. So just look at T, the super translations. If you just look at T, the vector field is this. So zeta of T is T times del U minus 1 over R divergence of T and 1 over 2 Laplacian on T. This is in the R direction. This vector field preserves Bondi form. It preserves asymptotic boundary condition in a way such that when you apply this, the asymptotic fields change. Okay? The boundary conditions are preserved, but the asymptotic field changes. So one can write down how this vector will act on various quantities. One can write down how it will act on the Bondi mass. One can write down how it will act on the angular momentum aspect, how it will act on the C tensor, and so on. So all those formulas you can find in the reviews that I mentioned. Perhaps what is very interesting is that this is the only formula that I have written here for the action of the super translation field on the super translations on the asymptotic field. The scalar field that I discussed, Okay, the CAB becomes derivatives of the scalar. So the action of super translation on the scalar field is very simple. Just delta T of C is T. Okay, this is just this. Okay, so now why are they called super translations? What you can do is that you can take partial Z, like translation in the Z direction, and you go to radial coordinate, convert into r theta phi, and then you convert into u r theta phi coordinates. If you do that exercise, you will see that this form is what partial Z takes. Partial Z will be like cosine theta del u minus 1 over r, divergence of cosine theta del a plus 1/2 Laplacian acting on cosine theta del r. Okay, like this. Similarly, if you do for partial x, you will see that it takes this form with various terms given by this equation. So for translations, you see that, I mean, with this small calculation, you see that for translations, the vectors takes this form. And since this is a generalization of our translation, because t is an arbitrary function, these are called super translations. Okay, so now one can construct charges for various these symmetries. Let me not go. Okay, so the charges in general relativity is the big subject in itself. I mean, one can give many lectures on this. I will just try to be very simple. So I will just say that the super translation charge Q of t, the first variation of that charge is given by first variation of this quantity. And then there is this term which cannot be written as delta being pulled out. So you cannot put the delta here. The delta has to be inside here. So this is the non-integrable piece. So this is the integrable piece. Here you can pull out the delta, but here you cannot pull out the delta. So this is the non-integrable piece. This non-integrable piece tells you about the flux of super translation charges. How the super translation charge changes when you go from one point to another point at null infinity. So here is the picture. So if you go from point 2 to point 1, there will be some gravitational radiation coming out. This gravitational radiation may carry super translation charge, and the change in the super translation charge will be captured by this expression. So this is the Bondi news multiplied with the CAB. Okay, but when you go to spatial infinity, then as we discussed, the News tensor goes to 0, and then this becomes a total charge. You can remove the delta. So if you remove the delta, then Q super translation charge is just the integral of the super translation T against the Bondi mass M. So it's just the T times the Bondi mass M. So what this is telling us is the moments of the Bondi mass. The super translation charge captures the moments of the Bondi mass at spatial infinity. Okay, so this is something I discussed. So Qt2 is Qt1 minus flux through the future null infinity. Similar formulas one can write at past null infinity, and then one can ask whether this expression matches at future and past. Okay, so again, this is some topic that people have worked on a lot in the last few years. Okay, now let me briefly mention about the Lorentz algebra. So Lorentz algebra has t equal to 0. Only the vector field r is non-zero now. For the vector field r non-zero, this is the form of the vector field that preserves the Bondi gauge and the Bondi boundary conditions. So see, this is Ra del A. This is why it is a rotation. I mean, R phi del phi. The simplest case will be just del phi. And then the radial part, the vector has some radial part which is related to derivative of the vector r, and then it has some u part which is also related to the derivative of the vector. And as I said earlier, these vectors satisfies the conformal killing equation on the two sphere. So there are 6 solutions, and these are the 6 generators. Okay, so together with the Lorentz symmetries and super translation, what we have is something called BMS4. So this is the Bondi-Sachs group. 4 because in the literature now people are discussing BMS in different dimensions, BMS3, BMS5, BMS6, whatever. And this is the canonical BMS group. Okay, there are many generalization of this. The generalization I'm not discussing in this lecture, but this is the old canonical BMS 4 group. Okay, B. Okay, so now this is essentially all I wanted to say. So now I have a few slides on modern developments, but I'm happy to take questions and yeah.
Yeah, there is one question. How is the third written in the coherent form? I'm not sure which one he's talking about.
Yeah, no, this I answered. This I answered. So this student was, this person was referring to this derivative condition, the Lie derivative acting on the derivative. So
okay. Understood.
The physical quantity the super translation charge correspond to. This is a difficult question. Okay, for translations, it corresponds to the momentum. So translation charges are momentum, and we understand what the physical interpretation is. Now, for the more general super translations, the physics understanding is not so obvious. What people have discussed is that these super translations correspond to some memory effect, but that is some topic that I will not discuss in this lecture. I have not prepared slides on that. Yeah, so the physical interpretation of super translation charges is not completely straightforward. Okay.
If there is any questions, please you can unmute and ask directly.
Hello, sir.
Yes.
I have a question.
Yes.
So, can you tell more about the news tensor? Means actually the gravitational waves are carrying the information, right?
Yes.
From horizon to null infinity. So at null infinity, is there any receiver who is receiving that, or like?
Yeah, exactly. So what will happen is maybe this diagram is better. Yeah, this diagram. So suppose you have a detector at u equal to u2. So at this location. So at this location, you will measure, let's say, the Bondi mass. And you may ask, can I compare this at location u equal to u1? So the idea is that the difference between the Q2 and Q1 will be given by the integral of the new tensor. It will be related to the integral of the new tensor along this U2 minus U1 length of this null infinity. Yeah. So the new tensor actually tells you information about how much gravitational radiation is coming, and using that you can compute the energy of these gravitational waves that are coming.
Okay, thank you.
Hello. Can I have one small question?
Yes.
Yeah. Go ahead.
Yeah. So I was just wondering about this boundary condition that you have taken,
Yeah.
which also, I mean, gives rise this conformal killing equation. Okay. So as we know that there is some extension of BMS group recently that have been achieved.
Yeah.
So this conformal killing equation had also been recovered there probably.
Yeah.
But probably the smoothness of this vector field was relaxed, right?
Yes. So there are multiple extensions people have discussed. One extension discussed by Barnich and Prasad is you look for solutions to this equation which are not necessarily smooth, holomorphic functions on the sphere. Monomorphic. So when we are looking at smooth functions, we are looking at holomorphic functions. But when we look at non-smooth functions, these are meromorphic functions on the Riemann sphere. And people have written many papers on this. There is another set of boundary conditions that people have proposed. People say that you do not set the metric at infinity, the sphere metric to be gamma AB, you allow that gamma AB to change. And if you allow that gamma AB to change, then this equation has no meaning because gamma AB is changing. So this equation just becomes, some sort of, it doesn't tell you anything. So then this gives you an extension of the BMS4, which has been called the generalized BMS, in which you allow for arbitrary vector fields on the sphere to be your asymptotic symmetry. So there are many generalizations there are other generalizations, there are like many versions people have discussed, but all those versions, in my opinion, have one problem or the other. So I don't, that is a sort of a digression from my main lecture that I want to give. So I don't want to go into the problems.
So, instead of this conformal killing equation, if one solves killing equation, so you will get 3 generators, right? On sphere.
Yeah, but that is too restrictive. You want to, you see, the conformal killing equation comes because you want to have freedom in redefining your u coordinate and radial coordinate and things like those. So preserving the Bondi form, preserving smoothness of the metric at the sphere, this is the equation you will get.
Okay.
Yeah. Okay, so this is the reason I said I wrote it in capital. This is the old canonical BMS4 group. There are many versions of the new BMS group which I'm not discussing.
So would you be able to tell something about the conservation of these charges, or supertranslation charge?
I said, yeah. So the conservation for supertranslation charges is not surprising. So the supertranslation charges at spatial infinity, they are completely integrable, and you can write down an expression for Q of t, which is just t times m. And you can ask whether this expression matches with something at spatial infinity. One can ask whether this matches with past null infinity. All those questions one can address. When you are at null infinity, then of course, since there is a flux, you cannot write down a full conservation. You can write a conservation law, but conservation law is in this sense, that you can relate Q2 to Q1 via a part, which is this flux relation. Yeah.
Okay.
Yeah. Ryan is saying, I guess this is Ayan Chatterjee.
Yeah, can you discuss some of the recent things that are going on? So, yeah.
Okay, so the subject has received great interest in the last few years. I mean, the subject was considered to be very difficult and exotic 10 years ago, but now, like string theorists and relativists and people in between, like all sorts of mathematical relativists, everybody's, lot of papers and many people are working on this subject. So these are the 4 or 5 main topics that people are discussing. So one is matching across past and future null infinity. So this is a topic which is of great interest. It's rather surprising that relativists did not address these questions in the 60s when they discovered the Bondi-Sachs formalism. Only very recently, the interest in this subject has started, and a lot of papers and a lot of progress. This is some subject that I have also worked on. This is very interesting developments have taken place. Okay, so now as Srijit was saying, there are many extensions of this BMS symmetries, extensions of asymptotic symmetries to all sorts of extensions people have discussed, generalized BMS, extended BMS, holomorphic BMS, like lots of extensions people have discussed. In my opinion, most of the extensions have one problem or the other. So for every extension that people have discussed, you can find a paper which argues that that extension does not make sense. So like there is a lot of discussion in the community on this. There are also extensions in other directions, like extensions in logarithmic directions and so on. Okay, then there is a lot of interest in relation to soft theorems from quantum field theory. relation between soft theorems in relation to asymptotic symmetry. So this is also a subject that has received a lot of attention. People from Chennai have worked a lot on these things. Then memory effect is another topic which has received a lot of attention. This is related to the interpretation of super translations, and as an extension, relation to extensions of these asymptotic symmetries also. Okay, so for the interest of time, I will not go into the details of the above topic. There are another topic that has received a great deal of interest in Bondi-Sachs formalism is de Sitter gravity in Bondi gauge. So this is the subject. This is another one of those subjects that I have worked on. So let me say a few things about this here. Okay, so Bondi-Sachs in de Sitter. So Bondi-Sachs formalism famously clarified many aspects of gravitational radiation theory in flat space. Okay, one can say that this was the formalism that led to a lot of development in theoretical aspects of this gravitational radiation theory. Now, it is widely believed that the same formalism can be useful in other spacetimes, in particular in de Sitter spacetime. And in the last 5 years, people have tried to make sense of this, especially after the work of Ashtekar, Bonga, and Kashyap from 2015. Okay, so de Sitter space is like so, and what we are interested in is UR theta phi coordinates. UR theta phi coordinates cover some part of de Sitter space which is drawn in this lines, by these lines. Okay, so we want to focus on the diagram where future null infinity is there. So this full line is there, and some part of this spacetime will be covered by UR theta phi coordinates. Okay, so what we will do is that we will write the metric in Bondi gauge with the determinant condition. Okay, so there are variations on this. There are other people who have written papers. We do something else, but what I will discuss is we write the metric in Bondi gauge with the determinant condition. Okay, so these are the functions. So the beta is the function which enters the UR component, and the V is the function that appears in the UU component, and GAB is the metric on the sphere, and UA is the function that appears in the cross terms between U and XA. Now, as before, one has to do an equation of motion analysis in a sequential order. This has been done in a great detail in number of papers. Equation of motion analysis reveals that this function beta starts with 1 over r squared. And the U function has more integration constant than you might naively expect. So U function has this UA0, which is not fixed by the equations of motion. The next term is fixed by the equations of motion. And then there is the angular momentum aspect, which is not fixed by the equations of motion. And then there are terms which are fixed by the equations of motion. Okay, so there are two functions that appear here. So UA and NA. So NA is the angular momentum aspect, and UA is the arbitrary set of functions which are allowed by the equations of motion. Okay, so this may look a bit surprising, but there is a very deep physics here. So the physics is that in de Sitter, both normalizable and non-normalizable modes are required to have any dynamics. If you turn on only non-normalizable mode, then of course you don't have any dynamics in de Sitter. If you turn on only normalizable mode, then finally it so happens that there is no dynamics in de Sitter again. So in order to have any sort of gravitational waves or any sort of gravitational dynamics happening in de Sitter, you must turn on a combination of normalizable and non-normalizable mode. And this is the reason both NA and UA appear in this Bondi expansion. So NA is the normalizable part and U is the non-normalizable part. So both these things have to be turned on. Okay, so moving further, so we look at the equation of motion analysis for the function V. So because we are in de Sitter, so there is this lambda term which is related to de Sitter. Then the r square terms is fixed by the U, which we have already said that it is free. And 1 over r, the next term, the r term is fixed by C. Okay, and then a new function appears. This function is as in flat space. This is the Bondi mass aspect. Okay, we carry on. We have GAB. GAB has gamma AB, which we have chosen to be round metric on the sphere. One can relax this, but there are good reasons not to relax this. So gamma AB is the round metric on the sphere, and then there is CAB and further things. If you go down in the expansion, this 1 over r cube term appears. This is the normalizable. This should be normalizable. Normalizable modes allowed by the equations of motion. Okay, so as before, the most important quantity is CAB. So CAB now is determined by U. So in flat space, remember CAB was a completely free independent data that you have to give. Here, it's not the case. The C function, the C tensor is determined by U. So the equation that CAB satisfies is this. CAB is derivative of U, a symmetrized derivative, and there is a divergence here. So you see, this is very interesting. All the information that CAB carried in flat space, I said CAB was the most important quantity that carries everything about information about gravitational radiation. In this context, all the information in CAB is contained in UA0. So CAB is symmetric, traceless, remains an arbitrary function of the retarded times and angles. All that is true, but all the information about C is contained in this U. So U is the correct analog of the radiative field in de Sitter spacetime. The News tensor. The News tensor, unfortunately, is not such simple, and unfortunately, still after about 5 years of discussion in the literature, there is still no canonical simple definition for News tensor in the literature. The one of the nicest expression is like so, that NAB is derivative of U, derivative of CAB, and then there are a lot of other things, which is like Lie derivative of CAB in the U0 direction, some divergence of U times CAB, and so on. And if one does the analysis, then one finds the evolution equation for the mass aspect, evolution equation for the angular momentum aspect, but these equations are a lot more complicated, and a lot of things not completely sort of sorted out about what these various terms mean and what is the physical understanding of all of this. This remains to be explored. Okay, the energy is given by the integral of the mass function. So this is very nice. This is how the mass function is defined, is designed. And similarly, the angular momentum is given by the integral of the angular momentum aspect, but this is roughly true. I mean, again, there are subtleties about the extra terms, and for the extra terms in flat space, there are many papers discussing those extra terms. In de Sitter, there are not so many papers. People have not gotten around discussing the angular momentum physics in de Sitter yet. Asymptotic symmetries and other details are essentially research topics. I mean, there are papers which disagree with each other on basic premises. So asymptotic symmetries in de Sitter is indeed unsettled topic. The most important question in this subject is positivity of Bondi flux. This has been partly addressed, but not completely. And if you're interested in this, this is the paper. Beatrice Bonga will give a talk in this conference at the end of the conference. This is from last year, June 2023. In this paper, you can find all the important references on this subject. And this is all I wanted to say. So thank you.
Okay, so thank you, Amitabh, for nice discussion on this difficult topic. I hope students have understood a bit of it. So if you have any questions, maybe 1 or 2 maximum question you can take. So if anybody has any question, please go ahead and ask. There is one question in chat box. Maybe you can look at it. Yeah. Srijit has asked.
Recording stopped.
There is a notion of supermomentum.
No, I just commented against a question. So okay. What is the physical meaning of the charge correspond of super translation? So somebody was asking. So I hope at SPI there is a notion of super momentum, right, Amitabh?
Yeah, and I mean, there is a note, but I think the question is, what does super momentum mean? That is the question.
Yeah. So that requires a little more detailed discussion, but I think you can tell, please.
No,
I mean, some center of mass. I mean, in the field theory, we know that there is some notion of center of mass charges, etc. I mean, charges corresponding to the translation of that. So whether that is related to this, I don't know.
Actually, I also don't know. I would say that there is a lot of literature on this. I would say that this memory effect is perhaps the best way of understanding what the super translation charges are.
I have one quick question. So when Bondi started his calculations, he threw out these log terms, right? So when you have log terms at this polyhomogeneities in the scribe plus that people actually talk about. So do they take these log terms as well when you do those things at scribe plus?
Yeah. Okay, so the log terms are very important. They are unfortunately not fully analyzed yet. So indeed, in the original Bondi papers, in the first 9 papers or so, they did not discuss the log terms. But I think from 12th paper onwards, they started discussing the log terms. More recently, people have understood that one cannot get rid of log terms. Log terms are important and one should deal with them. People in Paris and people in Brussels have written papers on what should be the right boundary conditions to include. But the trouble with the subject is that so far there is no understanding of how the log terms at spatial infinity are related to log terms at null infinity. So this is where the subject sort of has gotten stuck. It is not clear. The transition of boundary conditions from spatial infinity to null infinity is not at all clear. This is what I would say.
Okay, thank you.
Maybe we can move on. There are some questions or doubts in the chat box. Maybe we can discuss later. If you quickly can answer this question, then it would be nicer.
I have answered all the questions. What is the memory effect? The memory
some general question. Basically.
The memory effect is like, suppose you have 2 satellites and gravitational wave passes through these satellites. Then what will happen is that the location of these satellites will change. And this is a permanent change. Because of the fact that gravitational waves have passed, the location of these satellites have changed. So one can ask, can I infer some property of gravitational waves, or can I infer some property of space-time in which the gravitational wave phenomena is happening by measuring the old distance and the new distance? And this is what has been called the memory effect.
Okay, Amitabh, thanks for this nice discussion on this topic.
Thank you.
Let's thank Amitabh again for his nice discussion. Maybe we can move on to the next talk. Again, it is basically the continuation of the talk that he has given. So maybe Sitender, are you there?
Yeah, I'm here.
Yeah, can you please share your screen?
Okay. Can I be made? I'm not able to.
Yeah, Srijit?
Yeah, I am.
So, I think you have to make him co-host or something.
Yeah, now I can. Yeah.
Yes.
Okay.
Yes. Yeah, we can see. You can see. Yes.
Yeah.
Yes, great. So let us begin. I think it is just the continuation of the previous one. Without any further delay, Sitender Kashyap, please go ahead.
Yeah. So thank you again for giving me opportunity to present this lecture. So let me start by Let me start by making some comments about on yesterday's lecture. So there were 3 questions that were asked. So in order to answer them, there was this question about killing vectors in xAct. So I did a search, and then it says that in extras, this package, if you load, so there you can find some information about about killing vectors. So for example, if I do this search,
excuse me, just wait. Excuse.
Can you hear me?
I think it is not being recorded. So yeah, so this is not being recorded. If sir can just enable recording, can you just wait for a moment?
Okay, yeah, sure.
I think
Recording in progress.
Okay, so shall I start now?
Yes. Yes.
Yeah. So so if we load the package extras, and then we suddenly see that there are this, like for example, if we just try searching killing, so it tells us about like killing vectors of. So what this command does is it defines that a particular tensor is a killing vector of some metric. Then if you search more, for example, killing vector q, so what it says is that if it checks whether a given vector is a killing vector or not. So I think if one digs deeper, they can find out whether given a metric, whether a vector is a killing tensor or not. But the inverse question, I do not know how to answer. Like given a metric, how do we really go about finding out killing vectors? Maybe the answer already exists. That I do not know. The second question was about tetrads in xAct. And here there indeed is a package called but other than Mathematica, there is another computer algebra system called Cadabra, and that takes care of tetrads and tetrads. The older version of Cadabra, called Cadabra 1, had all of its functional. The newer version, Cadabra 2, still has to like upgrade these commands, but Cadabra nonetheless is a very useful software as it allows much more flexibility to the user. But there, the user has to work a little more to define to get their work done, because many of the things are not that automatic. But then it allows more flexibility. I mean, so many things which are not possible in xAct can be done. Finally, there was a question about working with covariant derivatives, which when acting on a metric do not vanish. So is it possible to program such theories in xAct? After a bit of search, I could not find such a thing, because xAct perhaps requires matrices to be metric compatible. But maybe this is just my limitation. Maybe the question can be raised in the xAct Google forum, which is. And finally, there was one issue about showing how to obtain equation of motion for higher order gravity theories using extras. This was left yesterday. This we can go back again. Anyways, I'm sharing my slides. So if one is interested, they can directly learn from there. It's a very simple thing. But let's continue with today's talk. If there is time, we'll get back to this. Okay, so with this, let us start today's session.
Yeah, Sitender.
Yeah.
Maybe we can take one question that if you have looked at it, so this is relevant to this.
How is it? So
can't you do the tetrad calculation in xAct or something?
Yeah, it can be done. It can be done. As I mentioned, this.
Okay.
There is a package called npghp. So this is the link. Here you can find the documentation. So there I can see that there are tetrads, etc. But maybe not of very much generality. Maybe there will be some restriction. Okay. So that's our.
Okay.
Yeah.
Go ahead.
See is how we can use xAct to learn some physics in Bondi gauge. So in this session, we present some of the details of how we can use xAct for computations involving Bondi gauge. We shall be following three references. The first reference is aspects of BMS CFT correspondence by Barnich and Prasad. The second is the lambda BMS4 group of DS4 and new boundary conditions for ADS4 by Jeffrey Compare, Adrian, and Romain. And the third paper is the partial Bondi gauge, further enlarging the asymptotic structure of gravity by Mark and Celine. Yeah, so these are the primary references that we shall be using. So programming this in xAct involves two steps. The step one is essentially to verify the results of the Christoffel connections and the rich tensors that have been given in this first reference, so that we also get a handle of whether it really is programmable in xAct or not. So this is our first goal. So so let's just briefly recall what Amitabh already mentioned in his first half of the lecture. So the metric in the Bondi-Sachs form is of this form. Here we see that there is no GRR component or GRA component. So these are like three equations. This is one equation. These are two conditions. And then there is the fourth condition, which can be written in two equivalent forms. This form is called differential form, and this is the algebraic form where we demand a certain property on the determinant of this round or this two-dimensional metric along the x direction. Now the point is, any metric can be brought in other form. The transformations might be very hard to get, but this is a general result. Any four-dimensional metric can be brought in this form. In the above, beta, v, UA, and GAB are arbitrary functions of the Bondi coordinates U, R, and XA. Further, this additional condition, this metric condition, essentially implies that CAB. Okay, I think. I see. So here I should mention that there is this expansion of this GAB can be readily expanded, and yeah, this can be readily expanded, and the determinant condition on GAB then forces certain relations among these objects D, E, F, and these are all rewritable in terms of C and E, etc., etc. So these are some of the conditions. I mean, to begin with, these things are arbitrary, but determinant condition implies, for example, that CAB, this guy, is traceless with respect to QAB, and that DAB is related to CAB, and there is a trace-free part. So this curly D. Similarly, E is also related to curly D and C, so on and so forth. So, yeah. Now, so this is one thing. So we expanded the metric like this. What about the other fields? So for the other fields also, as Amitabh has mentioned, we will expand them in 1 powers of 1 over R. So for example, beta is beta naught plus beta 1 upon R, beta 2 upon R squared, beta 3 upon R cubed, and so on and so forth. Similarly, UA can be expanded as U naught A, U1A upon R, U2 A upon R squared, and so on and so forth. Finally, V can also be expanded in powers of 1 over R, V naught, V1, V2, V3, etc., etc. Now, so with these expansions, our goal is to substitute all of them in the Einstein equation, which with some cosmological constant term, lambda, and demand that the Einstein equations are solved order by order. So, the idea is not all. All these arbitrary tensors CAB, DAB, E, beta 1, beta 2, beta 3, U naught, U1, etc., etc. All of them, if we demand them to be arbitrary, these equations will not be identically zero. And demanding that Einstein equation do get solved, they fix some of these functions, like for example beta 1, beta 2, or they relate these quantities among themselves, as Amitabh had already mentioned in his talk, or showed in his talk. In this talk, we will see, for example, how we can get those relations explicitly by making use of xAct. Yeah. So now the point is, if we very naively just give it to Mathematica and ask, substitute all of these equations in all of these equations, and then say brute force just solve it, it will not be able to do that. If there is a supercomputer really powerful, maybe it might be possible, but it's really complicated. So what Bondi and collaborators came up with is something called the Bondi hierarchy. And in Bondi hierarchy, what it says is that there is an order of solving the equations that simplifies the determination of solution space. So let me very quickly recall what are the equations that we need to solve first. So to begin with, so there are like these equations. So equation involving GUU, GUR, GUA, GRR, GRA, and GAB, all of them equal to 0. So the idea is to first solve the equations that do not involve these lambdas, which we can see from here is GRR and GRA. So the first equation, GRR, solves for beta, and the latter solves for UL. Latter means this GRA equal to 0. Integration of the second of the above equation, that is GRA equal to 0, leads to an integration constant called NA, and this is interpreted as the angular momentum aspect. The time evolution of this NA is determined by another equation in the later in the Bondi hierarchy, which is GUA plus lambda GU equal to 0. So having solved, gotten the contents from the equations that do not involve this cosmological term, we solve for lambda dependent equations of motion. So first we solve for GUR, this guy, equal to 0. And its contents are same as GAB, this equation, as Amitabh has already mentioned in his lecture. But the point is, these equations give rise to another integration constant called M, and which is interpreted as the Bondi mass. Finally, having dealt with two of these equations, we are left with just these two equations, GUU and GUA. The former, this guy, determines the mass loss formula, and the latter, this one, determines the evolution of angular momentum. Now, this is essentially the theory, and we need to implement this in xAct. As we can see, the situation is neither fully covariant nor fully coordinate dependent, because it is not fully covariant because we are not using full 4-dimensional indices. We are mixing things up. U is there, capital A is there, and R is there. And it is also not fully non-covariant because coordinate dependent, because there is this covariance in that XA directions. So because of this, it is not very easy to see how to program this. either using extensor, which takes all components, which is like fully covariant, or xcoba, which is like fully coordinate dependent. So we'll have to be somewhat smart to keep using covariance in the transverse direction, that is along xa. So okay, so with this theory, now we are ready to see how to go ahead and do things in xAct. So the basic algorithm behind the partial covariance in the theory. So the idea is to notice that the four-dimensional metric is the one that was written above, can be written like this. The inverse of such a metric is this. Now the basic idea is to treat the unknown fields beta, v, u as fields in a two-dimensional manifold of which the metric is GAB, and convert all the 4D quantities in terms of covariant derivatives and Christoffel connections of the two-dimensional transverse metric GAB. And this covariance, this partial covariance, was already achieved in this first paper by Varnish and Prasad. And the authors in this paper, they defined, for using certain notation, some additional fields, KAB, LAB, and NA. KAB is essentially the R derivative of GAB. LAB is essentially U derivative of GAB. And NA is essentially related to U. It's some combination. Okay, so after this, the equations are solved using Bondi hierarchy mentioned above, with radial expansion of metric G as given above. Once we do this, once we have readily expanded GAB, the raising and lowering is done with respect to the leading part of G, which is QAB, as you can see here. So all the raising and lowering will be done once all of this has been substituted with respect to QAB. Okay. So coding in xAct. So first we shall verify the results of one. And once we are confident of the expressions, we follow the Bondi hierarchy, but with the metric QAB, the leading part of the full transverse. In the above, all indices are raised and lowered with respect to in this particular. So there will be two mathematical notebooks. The one which I am using right now. Here we will be verifying the results of one, and the metric will be two-dimensional metric GAB, and in the next notebook the metric will be QAB when we actually illustrate the Bondi hierarchy. Okay, so with this let us set up the definitions. So yeah, so let's call the packages. So now there is this first command, preprint string dollar indices. This, as we saw yesterday, this is to ensure that when Mathematica or xAct is doing the computations, which involves dummy indices which have dollars, this will like remove them when the output is shown to us. There is another command that one has to use, which is to set options for the two canonical. Yeah, so there is a command canonical which was very useful, as we saw yesterday, but this has a specific feature which we do not want, and what is that feature? Let's see it by example. So before that, let's define two parameters, U and R, which are the coordinates of the four-dimensional metric or of the space-time. These will enter as parameters in the two-dimensional theory that we are considering. So the idea is we define a two-dimensional manifold, M2, which is two-dimensional, and with these indices, and it has a metric which has determinant +1, and the signature is +1. And it has covariant derivative represented by CD, and we will print it as G. And note that there are extra dependencies on this, which is R and U. These are treated as the parameters. So let's run this. Yeah. So Yeah, so, okay, so this comment I already made. So now let's go on defining various tensors that there are. Beta, for example, is a scalar, so we will define it as like this, but we demand that it depends on the manifold M2 along with the parameters Cu and R. So let's do that. Now, consider the following expression, Ex1. So what it is saying is that we are taking the covariant derivative of beta with respect to A and then multiplying with GA. Now, if we do a 2 canonical, because this guy is, so it's a covariant derivative, so it essentially raises the index and it becomes P. But now let's repeat the same exercise, but this time with a partial derivative. So you see what is happening. So it is saying that detected with metric incompatible derivative, partial derivative. Obviously, it cannot do that. It cannot just raise that index. So in order to deal with, to prevent Mathematica or xAct from doing such a thing, what we will do is we will switch off one of the features of 2 canonical, and that is that it is not allowed to use the metric to raise and lower indices on derivatives or anything else. Okay, so if I enable this option, see what is happening. So this time it did not complain, and it also did not raise or lower itself. So this option we will keep. Okay, and there is another important pitfall to avoid, which I'll demonstrate now. So xAct is very good at identifying an invalid tensor expression and its manipulation. Above, we saw how it did not blindly raise or lower indices on partial derivative and showed us error and did not proceed further with computation. The command that checks validity of an expression is validate. Let's just quickly search what validate does. So it essentially checks the tensorial expression, whether the tensorial expression have any unknown heads or does not have an object, with invalid index structure. So actually the point is, this is the problem that we will see. So let me demonstrate it, how it actually is happening. In our program, we found that xAct fails to warn us or the user in the following case. So let's define this tensor UA, which is in the Bondi metric. So let's define a quantity Ex. See, this is like product of two contravariant tensors, and this obviously is nonsense because in general relativity this is not making sense, and xAct is not warning us also. But the point is, we can check it again and ask next. So far so good. So if we use validate command, xAct does warn us. However, there is further subtlety. Let's take, for example, another example where we have UA and UA. This is a perfectly nice object and it's a scalar. But see what happens if we multiply these two. So once again, what it is doing, it is just collecting UA and squaring it. So this is again nonsense. Okay. But the more serious part is that if we take this expression and ask to validate, and this time it is not even telling us any error. Okay, so this is one very serious error which can lead us to like wrong computations. But fortunately, there is a way around this in the form of a couple of commands called put scalar and no scalar. So whenever we enter a scalar expression which is obtained by contraction of indices, like this is a scalar expression because there are A and A contracted, and we want to take powers of this such a scalar expression. What we have to do is we have to use a command called put scalar. So let me demonstrate it. So example 3, UA, and we call it put scalar. So what it has done is, see, it has made a bracket, and this time you see it has not done any nonsense. It's just cubing this scalar expression. And now we do no scalar. So what it is doing is UA, UB, UF, UF. So we can, let's say, call x to the power 30. And then we say no scalar. So you see, there will be no problem with indices now. So this is a perfectly this. So this was the only subtlety that we found encoding in xAct for this for the code. Okay, and with this subtlety out of our way, now we are ready to code further. So now let us define the other fields that I mentioned above. So there was this tensor scalar field V, and all of them depend on U and R. So these are the additional auxiliary fields that Varnish and Prasad define. And there is this additional label which we can ask, which we are asking it to print as K and etc. etc. Let's see, for example, we minus, let's say F minus G. So what it gives? So it is essentially giving us printing it as we expect. Okay, now Varnish Prasad have set these K, L, and N to specific derivatives. For example, once there is this command called index set delayed. So what it does is it takes a tensor expression and equates it to another tensor expression. So on the left hand side we have this tensor already defined, but this is equal to the partial derivative of G with respect to R. So now what you see, what will happen is if we let's say minus A minus B. So you see what it is doing. It is just taking replacing this expression with this. So this command index set delayed is like the usual command of Mathematica where we have dot and U rather than just the equality. So this is delayed in the sense it will not compute what is this derivative even if G was given. So that's the advantage of it. Okay, so then there are the other bunch of tensors which we can get from NKL, which have indices. Here all the indices were lowered, but we can have index down and up, etc., etc. So I'm defining further tensors for that. So with this defining the basic tensors, now let's define the 4D metric. So which, as we have already mentioned, we will think of it as comprising scalar fields B, P, and vector field U, and a metric field G. So now, yeah, so this is first part of our project to verify all the quantities given in Varnish and Prasad. So the idea is to arrange the four-dimensional metric in a 3x3 table, and the third row and column carry an extra index which varies over, takes two values. So this 3x3 table is essentially a 4x4 matrix in disguise. So but this is however in our head and not what Mathematica knows. So we then tell Mathematica to compute the Christoffel connections, the Ricci-Riemann tensors, using the usual formulae which we all learn in our general relativity courses, but in 3 dimensions. Like for example, okay, yeah, so this will become very clear once I move ahead. So now what we are doing is we are defining the components of the full 4-dimensional metric. So first will be like GUU, GUR, GUR, etc. Let me just print it and show to you. So these can be rearranged in terms of a list. So metric list. So for example, the lower guy, it is GUU, GUR, GUB, GUR. So notice that this is a scalar because scalar in our M2 manifold, the 2-dimensional manifold. This is also a scalar, but this guy has an index B and it's a vector. So that's how we have defined it. So GUA has a vector, etc., etc. So and similarly, we have inverse metric of this form. Okay, so now there is another command called make rule in xAct. So what it does is it okay, so let's take one simple example. let's cut it out. Sufficiently complicated example. Okay. Let's take a more complicated example. Okay, so this we did run, but now let's take this one. So what it is saying is, so the syntax is like this: make rule, and then we have a curly bracket. Here, what we say is that whatever tensor you want to equate to another tensor which has similar tensor structure. So this will set this guy equal to this exponential of 2 beta v by r plus g of this guy. So let's just see the example. So I have called this rule GUU rule. So if I take this, so you see what is happening is that it is essentially replacing GUU with. So we can collect all these rules that we have made for all the metric components and call them another rule, which is called Bondi rules, and the command is join. So this join essentially joins all the rules. And okay, some fancy way of just checking. So let's do this step by step. Maybe this one example.
Hi, Sitender.
Yeah, hi. Yeah.
Can you please take just one question is related to the current discussion? So,
I see. In LHS, in make rule, if you have two terms in LHS, one term in RHS, how to? Oh no. So you cannot have two terms. You have to have just one term. I think. Yeah, that's what I remember. Yeah. So
suppose we have two terms, then in that case, how do we write it?
I think you can do maybe step by step. First define another tensor which has. First define a tensor which is sum of these two terms. Okay.
Mm-hmm.
And then equate this tensor to whatever you want in the RHS.
No, like since this is a tensorial quantity within make rule, it automatically takes care. Like if you like if you have some different indices and you replace this make rule, then it automatically works. But if I am not using make rule and use normal things like two terms is replaced by one terms, then in that case it only takes care the terms which you wanted to focus, but the other terms it doesn't take care. But do you know, is there any similar way like make rule it should work? I don't know, like.
See, so let me try to understand the question. So you are trying to say, for example, here, if we have another thing.
Yes.
Okay, let's just try it straight away. Let's try it straight away. Okay. Let me just copy it and call it rule 1. Okay. And let's add another scalar. Okay. So GUR. Okay. So that's what it is. So it is saying that there are more than one terms. Okay, so you'll have to necessarily have one term. Okay, so now you want to see, you want to ask how can we do this, right?
Yes.
So let's just try it. So what I was saying is the following. Let's define another tensor. Let's say G U R. Okay, it's also a scalar, right? So and this depends on M, U, and R. So we have defined this, right? So next what we will do is make rule. And this time what we do is this guy. And on the RHS, we have this. Okay. So let's call it some other rule. Okay, this rule. So now we have a rule which is assigning this new tensor to these two tensors. Okay, but we already know what GUU for these the rules are. So for example, let's GUU are. So now let's say Bondi rules. sorry, G. I did not.
Yeah, this is slash dot, not double slash. Yeah.
We can do that. I mean, it can be done, but let's see. Okay. First, we have to give this thing, this rule. Okay, GUU R rule 1, so that it converts to this, and on top of this, then we give Bondi rules. Okay. Yeah. So this is what has happened. Okay.
Okay.
Yeah. So that's I think it's a little complicated. Where directly you cannot do, but you define another tensor which is essentially sum of those two, and then you can make another rule which will do that for you.
Okay. Thank you.
Okay. Yeah. Sure. Yeah. So with this, let us proceed. Yeah. So let's do one simple thing just for. Okay. So what I'll do is I'll just okay. Let's not do this. Let's just keep going because it might take some time. The point is the metric is in this form, and inverse metric is in this form. And then what we do is we just take this is like a 3x3 matrix. This is also a 3x3 matrix. And then we ask it to just multiply and do up our Bondi rules to canonical matrix form, etc. And then we find that it's essentially inverse. So, and we do the other way also. We again find that it is eventually identity. So what we have, essentially we have managed to tell xAct that these 3x3 matrices are inverse of each other. And now the idea is, so these guys, these 3x3 matrices, we'll take them as metric, okay? And what we shall do is, yeah, so let me just read it. Thus, we have managed to put a 4-dimensional metric in a 3x3 table. Now the idea is to simply evaluate the Christoffel connections, all the geometric quantities, the Riemann and Ricci scalar using this 3x3 table. And I'll not show, so we all know that how given a metric, how to calculate the Christoffel connection. So we are collecting, yeah. So let list 1, 1. Oops, sorry. Just okay. So here, what we will do is the following. Okay. So this list essentially. This is essentially a list which contains the information about the Christoffel connections. The relevant part for us is these 3 indices. These 3 indices will take value 1, 2, or 3, which will denote the values of like 3-dimensional Christoffel connections. These are some fake indices, but this one, for example, you can write any value to them. The only significance is that when the index is 3, for example, if C1 is 3, then we have to write here some of the 2-dimensional index. Similarly, for C2, we'll have, if it is C2 is some third index, then we have to write A, B, or whatever this 2-dimensional index. So let me just enter one example and then show to you. See list. Okay, let's say we want gamma 1, 1, 1. So it doesn't matter what the corresponding things are, 1, 1, 1. So it gives us the, this is like Christoffel connection G, sorry, gamma U, U, U. So you see, if I do a 2 here, it really doesn't matter. Nothing actually matters. This is part of the code. But when I have, let's say, 3 index here, then it is showing some error. So as I mentioned, it has to be, let's say, A. So suppose I want gamma A. This is gamma A U U. So gamma, you see there is this index A, and then UU index is there. Okay. Suppose I want it to be gamma BUU, so it does like that. Okay. So the idea is just take care of read it as you will do, like gamma 111, gamma 112, gamma 113, etc., etc. But only when the third index is involved, we have to bring in the indices that are on the 2-dimensional. So let's say this B F G, for example. So this will be, for example, gamma 333. So now you see that there is this dummy index which Mathematica has given, but then there is this upper B and then lower F and G. Just look at this. So this is how we code, okay? So with this, we will have all the Christoffel connections. So there are some other things which are there, but we'll not go into them. Our idea is essentially to directly see if the results of Varnish and Prasad paper we can verify or not, okay? So as I explained, this CC list has essentially all the Christoffel connections. So this 111 essentially means gamma UUU. So let's do one thing in detail, and then I'll just run others. Okay, so here we go. Oh, I suppress the output. So this is what gamma UUU looks like, and the so this G stands for capital gamma, okay, and this is one expression which we get using xAct, and this is standing for Varnish and Prasad B. And what they give in their paper is, So what they give in their paper is this expression. So now the idea is we have to see whether these two expressions are same or not. So naively they do appear, we cannot naively see whether they are same or not, okay? So what do we do then is we give the job to xAct. So let's say to canonical. So what it does is it rearranges, etc., and then it shows that the expression that we have and the expression that Varnish or Salt give, they are essentially same. So this we can do for gamma UUR, gamma UUA. So this we can keep doing for all the Christoffel connections. So with this we can verify. We verify that all the Christoffel connections are there. Okay. So let's not just keep running it. So this is all Christoffel connections. So we were able to verify them. Okay, so this is all the way to gamma ABC or ABF, for example. So having verified the Christoffel connections, eventually we want to use the Ricci tensor, which will go into the Einstein equation. So in order to do that, we once again using the metric. So Ricci scalar is essentially sum of 4 terms. So and we calculate them individually. This is part of CC list. Just a minute. Okay. Okay, no issues. The point is the following. So this CS, let's search for it. CS. Yeah, okay. Unfortunately, we'll have to run all of this. But let's see. Okay, so there is some internal thing which had to be done. So once we do that, now we can go to the Ricci. Yeah. So we calculate the Ricci. So now using our expression of CS rules, it's a little involved, but just okay. Sorry, actually everything had to be run. So there is some internal thing, internal code which had to be run, which I did not. Excuse me for this. Actually, it would take a lot of time if I explain this. So, okay, fine. Now with this, we are ready to define all the Ricci tensors. So let's say RUU. So this will be, once again, as I have said, if there are if the third index is not there, we can put anything in the first two guys. So oh god. I should have run everything. Let's run everything. Okay, great. So I think now it's working. Yeah. So, so for example, you see you're faced with this Ricci tensor, and this is a huge expression. And then you have RUR, which is also relatively shorter. Oops. Then you have RUA. Notice here we have 3 index, so we'll put A here. And these are all RR, RA, RAB. So this is the final Ricci tensor. So now in the Varnish-Prasad paper, they do give the expression for Ricci tensor. So which we just write in the xAct. And yeah, so for Varnish-Prasad, we do give the Ricci tensor. And so RUR for Varnish-Prasad is this. So let's just check one of them. Yeah. So this is the RUU that we had. This is Varnish-Prasad. If you just run it, then they show that it is 0. We did not run all of them, but as I am saying, all of them get verified. So essentially, we have verified the Einstein equations given in the Varnish-Prasad paper. So this sets up the thing that everything is fine. Yeah. So this is so I'm done with the first part of this verification. The next part is actually solving the Einstein equation. So yeah, before this, are there any questions? And how much time do I have?
Around 10 minutes.
Okay.
Any questions from the audience?
Okay, seems like
okay, Sitender, maybe you can just continue.
Yeah. So, okay, so let me share my second thing. Okay, so now we have used Barich sort, and then there are, can people see this? Is it visible?
Yes, go ahead, yes.
Okay, yeah, great. So now let me first, which color? Okay. Yeah, so now, so having solved for the Einstein, having found that Einstein equation, etc. are correct, now we go on to see how do we actually solve in the Bondi hierarchy. So there are certain notations that I need to use, and with this we will follow from the paper by Mark and Celine, where they use this compact notation, CAB is essentially CC, CAB, D is essentially CD, etc. And they also, the traces are denoted by without any indices. C is QAB, CAB, D is QAB, DAB, etc. etc. So we shall follow the notations there. So let's set the directory. Let's run extensor xAct. Once again, the standard thing which I defined earlier. So as I mentioned in the beginning of the talk, this part we will use the metric as Q rather than G. So there are some rules that we define that partial derivative of R is 0, for example, partial derivative of U is 0. And once again, we define all our metric, all our quantities. But this time, G has been defined as a symmetric tensor, not as metric, okay? And because we will expand it in powers of R. So this is to be noted. And similarly, in Mathematica, the capital C, capital D, and capital E are already built-in functions, so we cannot use them for the fields. So what we do is we essentially use small indices for them, but we can print them as capital as we want. So I define them. And G4, G5, and G6 are the expansions of the inverse metric at order R4, R5, and R6. So for example, if I input CAB like this, it is CAB. Similarly, there are the traces, as I mentioned above. So the traces I denote by C0 because these are scalars and represent them with capital C, capital D, capital E, capital F, etc., etc. And the trace-free parts of all the objects are denoted by curly D. This I explained in the beginning part of the session. So now what we do is we define some trace rules and some scalars. And then there are certain identities which Mark's paper gives for which pertain to this the tensor C. And then we had earlier seen that the metric condition essentially relates DAB, for example, D minus A minus B. See, this is essentially DAB, but we saw earlier that DAB is related to other quantities because of the determinant relation. So let's see that. So this was the relation, okay? So this is what I have essentially told Mathematica to do. And then there are this index set. So what it does is it takes some quantity and it sets it to certain quantity, okay? So there are some definitions which the scalars will be equal to, and I have quoted here. Now comes the main part. So here what we see is we make a rule for expanding the metric and the inverse metric, and together I call them metric expansion, full metric expansion. So for example, if I have the metric G minus A minus B, then if I ask it to do metric expansion, so it will do this thing. And similarly, if I have AB and I ask it to do IMET, it will take into account those things. Now the idea is to expand all the fields. So we expanded metric. Now let's expand the beta. So beta is expanded as beta naught, beta 1, etc., etc. Similarly for U. So U is essentially U naught, U1, U2, U3, and there are some log pieces which we will find that they go to 0. Now, so having expanded all the fields, the U's, the betas, the metric, and the V. Okay, so we will not require V in this lecture. So the point is, the first equation that we have to solve in the Bondi hierarchy is this RR equation, as I mentioned, and the second equation is at RRA. So this is the expression for the Ricci tensor. Now what we do is the following: we take this RRR and do substitute. For example, okay, let's do it step by step. I think I'll be done in 5 minutes. So let's take this RRR. So it gives us the expression in terms of the upper metric and the lower metric and beta. So what we will ask it to do is, let's say, metric expansion. Oops. So what it will do is it will expand the upper and the lower metric, but still you see that there is a beta here. So what we'll ask is to beta expansion. So it puts that thing again. So now this is the equation. And similarly, we do this for RRA. We expand also in, there is this U also there, which we expand. And then there is this expression for the inverse metric, and it is given like this. And we set them equal to this. Okay, so having in our hand all the definitions and expansions correct. So okay, this was just an example about how in the limit r going to infinity the series function behaves. So let's recall one thing. Suppose we have a function f of x, x naught, x 1000. So if we ask Mathematica to give us the coefficient of the second order term, so it is giving us that, okay? But notice that so this expansion is about x equal to 0. So the power which we want and the power which it gives is essentially same. But this is not the case when we have r going to infinity. For example, let's take example a little slowly. So there is this quantity GAB, the inverse metric, and you see this is expanded in powers of 1 over r. So now if I ask to do this series for this test, r going to infinity, and keep terms up to order 3. So it is not r cubed actually, it is 1 over r. So that's the point I wanted to mention. In the limit r going to infinity, it automatically assumes that the expansion is done in powers of 1 over. Okay, so that's the thing. So if I, for example, ask it to give me the coefficient of 5th power in 1 over r, so here we go, this is the thing, and it gives that. So this was one technical point. So with this, now let's try to do the thing for this, the RR expression equation. So I ask it to expand, let's say, to order minus 1000. That means r raised to power 1000. There is no such term. Similarly, you can keep verifying to, let's say, 100 or 10. There is no such term. 8, no term. So eventually you will come to minus 1. There is no such term. That means Einstein equation is getting satisfied automatically. At order 0, once again, there is it's getting satisfied. Order 1, it's also getting satisfied. This happens till order 2, but then once we come at order 3, what we find is that this equation gives us 4 beta 1. But beta 1 is the coefficient in expansion of beta. So in order for the only way for which the Einstein equation will get satisfied is that beta 1 must vanish identically. So this is what Professor Amitabh mentioned in his lectures and in particular today. So with this, having found this constraint, we set beta 1 to 0 and make a rule out of that. Now we go to next order. And this time our order 4, and there are various manipulations one has to do, which I do not have time to explain. If I do this, what I find is that at this order, the coefficient beta 2 appears along with the C, the most important tensor, as Professor Amitabh has been mentioning, the C. So once again, for this to be satisfied, this must be equal to 0. So what it tells is that this beta 2 must be equal to Cc by 32, and that's what we do. Similarly, we can keep going higher in order, and then we find what is beta 3. So beta 3 will be equal to Cd, so on and so forth. So similarly, okay, so point is there is just only one thing left, beta 4. So let's also do that. So once again, you see that at this particular order 6, we find that beta 4 is coming, and it is related to all the other fields that appear, and then we make a rule out of it. Okay, so now in final 2 minutes, I'll explain how we repeat the same process but with RA equation. So we find that at particular order r equal to 1, we get this equation. And then this essentially tells us that U1 is essentially equal to del A beta naught times this quantity. So similarly, we go another order, we find U2, but then this expression is complicated. But using xAct, we can convert all the partial derivatives into covariant derivatives, and then we get a simple expression. And then we can invert this equation to get what is U2. And we find that all of this matches with what has been given in the compares paper. So, so I think from here, we can keep going on like this, demanding that the Einstein equations are satisfied at each order, and we get various solutions. Of course, more technicalities appear as we go along, but the idea is clear. We keep moving brute force. So yeah, so that's it from my side. Like there are various other equations, and we can keep repeating this procedure. There will appear many identities that we'll have to take into account, but that's all. So, and yeah, and in particular, when you go and solve for this RUU equation, there you'll find that the Bondi mass loss formula appears for the curved spacetime. So that's the expression actually I was dealing with. There are a lot of complications there, and but I think those can be managed, and this is part of ongoing project. So yeah, so that's all from my side. If there are any other questions, I'll be happy to answer.
Okay, thank you, Sitender. So it's a nice presentation, and it's a nice way of doing tensor calculus in this Mathematica. So if anyone has any question, please unmute and ask. We can take few questions.
Hello?
Yeah, hello? Yeah.
Yes, Dibesh.
Yeah, I want to ask, what does this option do, metric on?
Oh, metric on?
Yeah.
Oh, yeah. So this what this option does is, suppose you define some relation, make rule is there, right?
Yes.
So in there, suppose you define something which is lower in the index. If you do not keep metric on, so it will not automatically raise or lower the. You'll have to define a separate rule. So let's directly see that. Okay. So let's go somewhere. Where it is. I think it was. Yeah. Yeah, here it is. For example, So actually, it's already clear. Yeah. Okay, so now what we do is, let's say E minus A minus B, and then we ask E rule. Oh, sorry. So it is giving us this, okay? But let's say if I make one of the indices up, so it's not automatically creating that. But if we had put metric on, I rerun that. Oops. So you see, it has automatically tried to raise the index, okay? If I try this, so it will do that, okay? So that's what this metric on option does.
So basically, it separates the quantity in terms of metric.
Yeah, exactly. Like for example, if I had not put it on, then I'll have to separately define for, other configurations. Okay. Like here I'm both covariant indices. The index, okay. But if I tell metric on, so then it will try to raise. Suppose I input this guy as contravariant index, so it will know how to raise this index. It will just put an additional index for raising this index H, and another. Oh yeah, so that's it. I hope it's clear, right? Okay. Yeah.
Recording stopped.
I have a question in the chat box. Could you please?
Yeah, sure. What is the difference between use this and this one? No, equal to, I think. See, the point is. So when you use this, so the functions are not explicitly evaluated. Only when you enter some. So this is like a delayed rule. Like whatever is on the RHS, it will not be computed as it is. And I don't understand what is this. Lakshmi Priya, can you?
Yes.
What is this colon?
You can see in your input 131, you wrote a semicolon in the last. So that means we can't see the output.
Oh yeah, you're right. Yeah, so this means we cannot see the output.
Yeah, my question is it the same meaning like the semicolon and the other symbol that I put in the chat box? Like
yeah, it's a semicolon. Yeah, exactly.
Okay.
Yeah, it's on the keyboard, right? Yeah.
And also I have another question that I wrote in the previous.
Okay. I have a general question. We already learned, for example, how to split the covariant derivative. My question is, how do we go reverse? For instance, suppose my expression contains many covariant derivatives. So I have we already. My question is, how do we go the reverse? For instance, suppose my expression contains many covariant derivatives and some other term. I can see from this expression, I can write it by some information. So you mean that there is a covariant derivative already present in the so let's try.
Like suppose I have a big expression which contains many covariant derivative and Christoffel symbol, and by looking this expression, I know I could write by combining 4 terms, I can write it. This is a curvature tensor term, or this is a Christoffel symbol. But how could I do this in Mathematica?
Oh yeah. So see, the point is the following. Suppose there is this command change. Yeah, I'm getting. You are saying that there is a bunch of terms present in your expression, which you may be able to recombine and rewrite it as covariant derivative, right?
Yes.
Yeah, so that's what I'm saying. This means that there will be some partial derivatives already present in your expression, right?
Yes.
So what you do is there is a command called change cov d. Okay, change cov d. So what it says is that let's take an example. Okay, PD minus a u of b. Let's say okay. So let's say ex change cov b. So in this expression, change PD to CD. So see what has happened is, so whenever there is this partial derivative, it has converted it to covariant derivative. Okay. Now there will be some compensating. If your expression is really rewritable in terms of only covariant derivative, there will be a compensating gamma with a plus sign, for example. Okay. And then your expression would be like, for example, let's take this itself. Okay. Plus let me just copy this perhaps. Better. Okay, and then let's say there are some other terms, CD or something else. Let's say C minus A
or can you write like Riemann CD and the other 4 indices?
It should have. Oops. Okay, so this should be partial derivative. PD minus a u of b, that will be minus b.
And could you please another term like the Riemann CD and the 4 indices?
Okay. Yeah, but you see, just this example. Okay. Here is this example. There is this partial derivative and then some Christoffel, right? So what I did is I just told it in this expression, you convert partial derivative to covariant derivative. Okay. And then it automatically realized that, okay, so there will come another, if it converts this to covariant derivative, then there will be a minus sign which will cancel, minus Christoffel which will cancel this, and we will be left with this expression. Okay, so this is a very simple example. Now you tell me what you want.
This is a simple example. You just convert partial derivative to covariant derivative.
Yeah.
So my question is, like the when you define the manifold.
Can I interrupt? Sorry. Hello.
Yeah.
Lakshmi, I think it is a little bit. The discussion is going on in a little more detail. Maybe is it possible to have a one-to-one interaction, Sitender, if you don't mind?
Yeah.
We are running already late.
Yeah, sure.
It is better if you do have a one-to-one interaction.
Yeah, sure.
Sure.
And maybe let me end the session and then maybe you can go ahead here.
Yeah. Thank you.
Okay, I think with this, let us end this session and also let us thank Sitender for this nice discussion on this package by which you can do a lot of tensor calculations. And with this also, let me thank all the speakers in the first session of this conference. And okay, so I think now it is a time for a break. And if there is any announcement from the organizer, please go ahead. Srijit, over to you. Srijit, are you there?
Yes, yeah. Let me thank the chairpersons of both the sessions, Arpan and Prasad, and all the speakers. And let me also thank the coordinators, Subhadip Sarkar and Divyesh Solanki, who are keeping me on my toes. Thank you. Reminding me for the recording.